In the vast darkness of space, orbits one small world that we call home. But beyond our sun lie trillions of stars, and orbiting those stars are worlds beyond imagination. Some scorching hot, some frozen solid, and even some that might harbor life. Welcome to Stellar Worlds, where we explore some of the most fascinating planets in the universe. Are you ready? Let's begin. To start today's video is WASP 33b, the extraordinary planet of fire. Imagine a world where the sky glows white-hot, where iron doesn't melt, it evaporates, where the atmospheric temperature exceeds that of many stars, where winds scream across the planet at velocities approaching the speed of sound, driving clouds of vaporized titanium and aluminum oxide through an atmosphere heated to nearly 3,500 Kelvin. This is not science fiction. This is WASP 33b, one of the hottest, most extreme planets ever discovered. A world that should not exist, orbiting a star that pulsates like a cosmic drum, challenging everything we thought we knew about planetary survival. This is the story of a planet at the edge of destruction, a laboratory for understanding physics under the most extreme conditions, and a reminder that the universe is far stranger than our imaginations. Our story begins in 2006, when a wide-angle search for planets, WASP, was systematically monitoring stars across the northern hemisphere, searching for the telltale dimming that occurs when a planet transits its star. WASP was designed to find hot Jupiters, giant planets orbiting very close to their stars. These planets are relatively easy to detect because they're large. They block a significant fraction of their star's light, and they transit frequently. But even among hot Jupiters, WASP 33b stood out immediately as something extraordinary. The star, cataloged as HD 15082, is located approximately 380 light-years from Earth in the constellation Andromeda. With a visual magnitude of 8.3, it's too faint for the naked eye, but bright enough for detailed study with modest telescopes. What made this discovery challenging and fascinating is that HD 15082 is not an ordinary star. It's an A-type star, significantly hotter and more massive than the Sun. A-type stars are rare hosts for transiting planets because they're usually young, rapidly rotating, and their surfaces are active, all factors that can mask or mimic planetary signals. Finding a hot Jupiter around an A-type star was unexpected. Before we can understand WASP 33b, we must understand its star, a star unlike our Sun in almost every way. HD 15082 blazes white-hot, radiating 5 times more energy than our Sun. Its surface temperature of 7,400 Kelvin makes it one of the hottest stars known to host a transiting planet. But there's something even more unusual. HD 15082 is a delta Scuti variable star, a class of pulsating stars that rhythmically expand and contract. Delta Scuti stars pulsate with periods ranging from 30 minutes to several hours. These pulsations are driven by internal pressure waves, essentially sound waves resonating through the star's interior. For HD 15082, we observe pulsation periods around 68 minutes. This makes detecting planetary transits more difficult because the star's brightness is constantly changing due to both pulsations and the planet's transits. Detecting WASP 33b required untangling 2 signals: the regular, repeating transit of the planet every 1.2 days, and the irregular pulsations of the star every 68 minutes. It's like trying to hear a steady drumbeat while someone is blowing a whistle right next to you. The pulsations add noise to the light curve, making the planetary signal harder to see. We had to develop sophisticated algorithms to model and subtract the stellar pulsations, revealing the underlying transit. After careful analysis and follow-up observations, the WASP team announced the discovery in 2010. WASP 33b was confirmed as a hot Jupiter, a gas giant approximately 1.5 times Jupiter's radius and 2.1 times Jupiter's mass, orbiting incredibly close to its host star. But the true extremes of WASP 33b would only become apparent through subsequent observations. WASP 33b orbits at a distance of just 0.0259 astronomical units from its star. That's 3.87 million kilometers, or about 2.6% of the distance from Earth to the Sun. At this proximity, the planet completes one orbit every 1.22 days, a year lasting just 29 hours. WASP 33b orbits closer to its star than any other known transiting hot Jupiter around an A-type star. At this distance, the tidal forces are enormous. The planet is almost certainly tidally locked, one hemisphere permanently facing the star, baked by relentless radiation, while the other side faces eternal night. But orbital distance is only part of the story. WASP 33b's orbit is retrograde. It orbits in the opposite direction to the star's rotation. This is highly unusual and provides crucial clues about the planet's history. A retrograde orbit strongly suggests that WASP 33b didn't form where it is now and migrate inward smoothly through the protoplanetary disk. Instead, it likely migrated through gravitational interactions with other planets or stellar companions, a violent, chaotic process that can flip orbital planes. This planet has a dramatic history written in its orbital architecture. The defining feature of WASP 33b is its temperature, a temperature so extreme that it blurs the line between planet and star. Based on the planet's distance from its star and the star's extreme luminosity, we calculate that WASP 33b's dayside equilibrium temperature is approximately 3,200 to 3,500 Kelvin. That's around 3,000 to 3,200 degrees Celsius, or 5,400 to 5,800 degrees Fahrenheit. To put this in perspective, this is hotter than the melting point of every metal except tungsten. It's comparable to the surface temperature of the coolest red dwarf stars. WASP 33b is one of the hottest exoplanets ever discovered, rivaled only by planets like KLT 9b and KLT 20b. At these temperatures, matter behaves in exotic ways. At 3,500 Kelvin, molecular hydrogen begins to dissociate into atomic hydrogen. Metal atoms, iron, magnesium, titanium, aluminum, exist as individual atoms or ions in the gas phase. Nothing is solid. Everything that would be rock or metal in the planet's interior is vaporized in the upper atmosphere. We're looking at a planet where the atmosphere itself emits visible light. It literally glows. Determining what's in WASP 33b's atmosphere requires transmission spectroscopy, observing the planet during transit and analyzing how the atmosphere absorbs different wavelengths of starlight. WASP 33b's atmosphere is a chemical cauldron. We've detected atomic species that would normally be locked up in rocks or clouds. Iron, titanium oxide, aluminum oxide. We see evidence for thermal inversion, where the upper atmosphere is hotter than the lower layers, likely caused by titanium oxide and vanadium oxide absorbing ultraviolet and visible light from the star. The atmosphere is so hot that traditional gas giant chemistry doesn't apply. Water vapor, carbon dioxide, methane, molecules common in cooler atmospheres, are absent or exist only in trace amounts. Instead, WASP 33b's atmosphere resembles a stellar photosphere more than a planetary atmosphere. If you could somehow survive long enough to observe WASP 33b's weather, which you absolutely could not, what would you see? Our atmospheric circulation models for ultra-hot Jupiters like WASP 33b predict supersonic winds, jet streams flowing at several kilometers per second. These winds are driven by the extreme temperature difference between day and night. Hot gas on the day side rises and flows toward the night side at high altitude, cools, descends, and returns at lower altitude. But the flow isn't smooth, it's turbulent, chaotic, generating massive eddies and vortices. At the terminator, the boundary between eternal day and eternal night, temperatures plunge by over 1,500 Kelvin. This creates tremendous pressure gradients and intense weather phenomena. We might see clouds of corundum, aluminum oxide, the mineral that forms rubies and sapphires, condensing as hot gas flows from the day side to the night side. These clouds would glow from their own heat, perhaps reflecting starlight in strange, iridescent patterns. Deeper in the atmosphere, where temperatures are lower, we might find clouds of iron and magnesium silicates, liquid droplets of molten rock falling as rain. But perhaps the most extraordinary phenomenon is the planet's thermal emission. WASP 33b doesn't just reflect starlight, it glows. Observations show that the planet emits its own light in the visible spectrum, making it one of the few exoplanets we could theoretically see directly, glowing like a dying ember. One of WASP 33b's most intriguing features is its atmospheric temperature inversion, a layer where temperature increases with altitude, rather than decreasing as in Earth's troposphere. We've observed WASP 33b during secondary eclipse, when the planet passes behind the star and we lose its thermal emission. By measuring how much light is lost at different wavelengths, we can construct a thermal emission spectrum, essentially measuring the planet's temperature at different atmospheric depths. What we found is that the upper atmosphere is hotter than expected, hotter than the lower layers. This inversion is caused by opacity sources, molecules like titanium oxide and vanadium oxide that absorb ultraviolet and visible light, depositing energy high in the atmosphere. This is similar to Earth's stratosphere, where ozone absorbs UV light, creating a warm layer above the cooler troposphere. But on WASP 33b, the effect is far more extreme. The temperature inversion has profound effects on atmospheric dynamics. It stabilizes the atmosphere against vertical convection, potentially creating distinct atmospheric layers with different chemistries. It also affects how the planet redistributes heat and determines which molecules can survive in different regions. Every 1.22 days, WASP 33b transits its star, blocking approximately 1.1% of the star's light for about 2.5 hours. This regular, repeating signal is the foundation of all we've learned about the planet. The transit depth tells us the planet's size relative to the star. WASP 33b's radius is approximately 1.5 to 1.7 Jupiter radii, making it one of the most inflated hot Jupiters known. This inflation is caused by intense stellar heating. The radiation pumps energy into the planet's interior, preventing it from contracting under its own gravity. But WASP 33b's transits reveal more than just size. The shape of the transit, particularly at the beginning, ingress, and end, egress, is affected by the planet's extended atmosphere. We observe extended absorption. The planet blocks more light at certain wavelengths than at others. This tells us about atmospheric composition and structure. At some wavelengths, we see the planet appears larger because we're probing higher atmospheric layers where certain atoms or molecules absorb light. To determine WASP 33b's mass, astronomers use the radial velocity method, measuring how much the planet's gravity causes the star to wobble. For WASP 33b, radial velocity measurements are challenging because the star is hot and rapidly rotating. Hot stars have fewer spectral lines, and rapid rotation broadens those lines, reducing precision. Nevertheless, we've measured a radial velocity semi-amplitude of about 295 meters per second, allowing us to calculate the planet's mass at approximately 2.1 Jupiter masses. Combining mass and radius gives density. In WASP, 33B's density is remarkably low, approximately 0.52 grams per cubic centimeter, less than half of Jupiter's. This low density confirms the planet is extremely inflated, puffed up by the intense stellar radiation. One of the most powerful techniques for studying WASP, 33b, is phase curve photometry, monitoring the planet's brightness throughout its entire orbit. As WASP 33b orbits, we see different hemispheres. During transit, we see the night side. During secondary eclipse, the day side is hidden. Between these events, we see varying amounts of the day side and night side, allowing us to map the planet's temperature distribution. Phase curve observations reveal that WASP 33b's hottest region, its hotspot, is offset from the point directly beneath the star. This offset is caused by supersonic winds that transport heat eastward, advecting the hotspot away from the substellar point. The offset tells us about atmospheric circulation efficiency. A large offset suggests strong winds and efficient heat transport. The amplitude of the phase curve, the difference between maximum and minimum brightness, tells us about day-night heat redistribution. For WASP 33b, the day-night contrast is extreme, suggesting that even with powerful winds, heat doesn't efficiently reach the night side. Recent advances in high-resolution spectroscopy have allowed astronomers to detect individual absorption lines from atoms in WASP 33b's atmosphere and, remarkably, to measure wind velocities directly. By observing at extremely high spectral resolution during transit, we can detect absorption from individual atomic species: iron, magnesium, calcium. But here's where it gets interesting. These absorption lines are Doppler shifted by the planet's motion and by atmospheric winds. By measuring these shifts, we can determine not just what's in the atmosphere, but how fast it's moving. Observations have detected blue shifted absorption, the signature of material moving toward us, with velocities exceeding 5 kilometers per second. This confirms the presence of supersonic winds racing from the day side to the night side. This is one of the few exoplanets where we've directly measured atmospheric winds. It's a powerful validation of our circulation models and gives us unprecedented insight into how these ultra-hot atmospheres behave. A planet orbiting this close to such a luminous star should not survive. The intense radiation should evaporate its atmosphere. Tidal forces should tear it apart. Yet WASP 33b endures. How? WASP 33b is losing mass. We can see it. The planet has an extended thermosphere where atomic hydrogen escapes into space. We estimate mass loss rates on the order of 10 to the power of 10 to 10 to the power of 11 kilograms per second, billions of tons every second. That sounds catastrophic, but the planet is so massive, about 400 times Earth's mass, that it would take billions of years to lose a significant fraction. But atmospheric escape isn't the only threat. The star's pulsations create periodic variations in radiation and tidal forces. The stellar pulsations might actually contribute to the planet's inflation. Each pulsation cycle deposits energy into the planet's atmosphere and possibly its interior. Over millions of years, this could provide an additional heating mechanism, explaining why WASP 33b is so puffy. WASP 33b could not have formed where it orbits now. Giant planets require large amounts of material, rock, ice, gas, that exist only in the cold outer regions of protoplanetary disks beyond the ice line. WASP 33b formed several astronomical units from its star, probably beyond the ice line where water ice and other volatiles were available. It then migrated inward through one of two mechanisms: disk migration or dynamical scattering. In disk migration, The young planet interacts gravitationally with the protoplanetary disk, creating spiral density waves. These waves exert torques that cause the planet to spiral inward over hundreds of thousands of years. In dynamical scattering, gravitational interactions with other planets, possibly in a multi-planet system that's now disrupted, fling WASP-33b onto an eccentric, highly inclined orbit. Tidal dissipation gradually circularizes the orbit while preserving the retrograde motion we observe. The retrograde orbit strongly favors the dynamical scattering scenario. WASP-33b's orbit indicates a violent past, probably a close encounter with another giant planet that ejected one planet from the system while sending WASP-33b inward. We're seeing the survivor of a planetary catastrophe. One of WASP-33b's most puzzling features is its large radius, 1.5 to 1.7 times Jupiter's. For a planet of this mass, standard models predict it should be smaller. Something is preventing the planet from contracting. The radiation WASP-33b receives is enormous, about 30,000 times more energy per unit area than Jupiter receives from the Sun. Most of this energy is absorbed in the upper atmosphere. But to explain the planet's inflated size, energy must somehow be transported deep into the interior, preventing contraction. How this happens is still debated. Proposed mechanisms include ohmic dissipation, electric currents induced by the planet's magnetic field interacting with atmospheric winds generate heat deep in the interior. Kinetic energy deposition. Supersonic winds in the upper atmosphere slow down as they sink, converting kinetic energy to heat at depth. Enhanced opacity. Certain atmospheric constituents increase opacity, trapping heat more efficiently than standard models assume. Tidal heating from stellar pulsations. The star's pulsations might drive tidal oscillations in the planet, dissipating energy. No single mechanism fully explains all inflated hot Jupiters. It's likely that multiple processes contribute, and the relative importance varies from planet to planet. WASP-33b, being one of the most extreme cases, is crucial for testing these theories. WASP-33b belongs to a rare class, ultra-hot Jupiters. These are planets with dayside temperatures exceeding 2,200 Kelvin, where chemical processes are fundamentally different from cooler hot Jupiters. Ultra-hot Jupiters are laboratories for extreme physics. At these temperatures, molecules break apart, atoms ionize, and atmospheric chemistry resembles stellar atmospheres more than traditional planetary atmospheres. They're also ideal targets for atmospheric characterization because their atmospheres are extended and their thermal emission is strong. WASP-33b ranks among the top 5 hottest exoplanets ever discovered. Its extreme properties make it invaluable for comparative studies. Every exoplanet is a natural experiment, a test of our theories of planetary formation, atmospheric dynamics, and thermal physics. WASP-33b challenges our models in productive ways. It forces us to ask, what are the limits of planetary survival? How do atmospheres behave at stellar-like temperatures? What processes inflate giant planets? By studying the extremes, we define the boundaries of what's possible and refine our understanding of more typical planets. Key questions WASP-33b helps answer. How do ultra-hot atmospheres redistribute heat? Phase curves and thermal emissions spectra reveal circulation patterns and the efficiency of heat transport. What molecules survive at extreme temperatures? Spectroscopy identifies which chemical species exist and in what abundance. Testing chemical equilibrium models. How does atmospheric mass loss proceed? Observations of escaping hydrogen and heavy metals constrain evaporation rates and mechanisms. What is the role of stellar pulsations? WASP-33b's unique host star allows us to study star-planet interactions in a pulsating system. Can planets survive such extreme irradiation? WASP-33b's existence demonstrates that planets can survive conditions previously thought uninhabitable. WASP-33b offers a unique opportunity, studying a planet around a pulsating star. The star's oscillations provide a window into its interior structure and affect the planet in ways we're only beginning to understand. Astroseismology, the study of stellar pulsations, allows us to probe the star's interior, much like seismology probes Earth's interior. The pulsation modes tell us about the star's density structure, rotation, age, and evolutionary state. For WASP-33, the presence of the planet actually affects the pulsations slightly, allowing us to study star-planet interactions in unprecedented detail. The star's pulsations might also affect the planet's atmosphere. Each pulsation cycle creates a periodic variation in the radiation the planet receives, potentially driving atmospheric waves or contributing to the planet's thermal budget. We're looking at a coupled system. The star affects the planet through radiation and tides, and the planet potentially affects the star's pulsations through tidal interactions. It's a natural laboratory for studying gravitational and radiative coupling. The James Webb Space Telescope is revolutionizing exoplanet science, and WASP-33b is a prime target. JWST's mid-infrared instruments can observe thermal emission from WASP-33b with exquisite precision. We can construct complete thermal emission spectra, identifying molecular features, measuring temperature as a function of altitude, and mapping heat distribution across the planet. For ultra-hot Jupiters, JWST can detect exotic species we've never seen before, perhaps ionized metals, complex oxides, or signatures of unusual chemistry. JWST observations could also detect detailed thermal structure, confirming or refuting the temperature inversion, rare isotopes and isotope ratios, providing clues about formation, variability in the atmosphere, indicating weather patterns or cloud formation, precise phase curves in multiple wavelengths, mapping three-dimensional temperature structure. WASP-33b is bright and transits frequently, an ideal target for JWST. Every observation reveals new details, new molecules, new surprises. I expect we'll be studying this planet for years. The next generation of ground-based telescopes, the extremely large telescope with its 39-meter mirror, the giant Magellan telescope, and the 30-meter telescope, will achieve spectroscopic resolution and sensitivity far beyond current capabilities. With these facilities, we'll detect individual spectral lines from dozens of atomic species in WASP-33b's atmosphere. We'll map winds with high spatial resolution, tracking how velocity varies with altitude and latitude. We might even detect aurora-like phenomena or magnetic field effects through Zeeman splitting of spectral lines. High-resolution spectroscopy could reveal wind patterns at different atmospheric levels, day-night asymmetries in composition, rotation rate of the planet's atmosphere, magnetic field strength through polarimetry, temporal variability, weather and atmospheric dynamics on timescales of hours. Could WASP-33b host moons or rings? Almost certainly not, but searching helps us understand planetary systems. The tidal forces at WASP-33b's orbital distance are enormous. Any moon larger than a few kilometers will be torn apart by tidal stress. Rings are similarly unstable. They'd either spiral into the planet or evaporate under the intense radiation. But we search anyway, because absence of these features tells us about the history and evolution of a system. Observations have found no evidence for moons, rings, or additional planets in the WASP-33 system. WASP-33b appears to orbit alone, a solitary giant, surviving in conditions that would destroy most objects. WASP 33b is a world that defies our terrestrial intuitions. A planet where the sky glows white-hot, where clouds are made of minerals, where winds blow faster than sound, where the temperature exceeds that of many stars. It is a world hostile to every form of life we know. No liquid water could exist. No organic chemistry could proceed. Nothing remotely resembling Earth-like biology could survive for an instant. And yet, it is a world of profound beauty. Beauty in its extremes, its physics, its very existence. It is a natural laboratory where we can study matter under conditions impossible to recreate on Earth. It is a reminder that the universe contains wonders stranger than fiction. Every exoplanet discovery expands our cosmic perspective. We once thought planets should be like those in our solar system. Then we found hot Jupiters and realized planets migrate. Then we found ultra-hot Jupiters and realized planets survive unimaginable extremes. Each discovery redefines what's possible. WASP 33b orbits silently, 380 light-years away, indifferent to our scrutiny. It has orbited thus for millions of years and will continue for millions more, until tidal decay finally spirals it into its star, or until the star exhausts its fuel and expands, engulfing the planet entirely. On a clear autumn night, you can see Andromeda high in the northern sky. Among its stars, too faint for any eye but a telescope's, shines HD 15082. And every 1.22 days, a world of fire completes another orbit. We may never visit WASP 33b. No probe could survive the journey, let alone the environment. But we can study it, understand it, marvel at it. This is WASP 33b, a planet of fire, a world of extremes, a testament to the diversity of the cosmos. And out there, among billions of stars and trillions of planets, what other wonders await discovery? The search continues. The universe, as always, surprises us. For our next planet, let's look at the discovery and promise of K2-156b, a world in the wilderness. In 2013, NASA's Kepler Space Telescope, the most prolific planet hunter ever launched, faced a crisis. After 4 years of unprecedented success, discovering thousands of exoplanet candidates, 2 of its 4 reaction wheels had failed. Without these precision pointing devices, Kepler could no longer stare unblinking at a single patch of sky. The primary mission was over. But rather than accepting defeat, the mission team devised an ingenious solution. They would use the pressure of sunlight itself as a virtual reaction wheel, balancing the spacecraft and allowing it to observe new fields of view. This was K2, the second light. From 2014 to 2018, K2 observed 19 different campaigns, each monitoring a new region of the sky for approximately 80 days. The mission discovered hundreds of new exoplanets, worlds that would have remained unknown if not for this ingenious resurrection. Among these discoveries was K2-156b, a super-Earth or sub-Neptune orbiting a distant star, a world that exemplifies both the diversity of planetary systems and the challenges we face in understanding them. When Kepler launched in 2009, its mission was revolutionary yet simple. Stare at 150,000 stars continuously for at least 3.5 years, searching for the periodic dimming that occurs when a planet transits its star. Kepler was designed to answer one of humanity's oldest questions: are Earth-like planets common? To do that, we needed to observe thousands of stars with extraordinary precision for years, long enough to detect multiple transits of planets in Earth-like orbits. The mission exceeded all expectations, discovering over 2,700 confirmed planets and revealing that planets are ubiquitous in our galaxy. But in July 2012, one of Kepler's 4 reaction wheels failed. The spacecraft could still operate with 3, maintaining its precise pointing. Then, in May 2013, a second wheel failed. Without at least 3 functioning reaction wheels, Kepler could no longer maintain the stability necessary for its original mission. There was real concern that Kepler's planet-hunting days were over. We'd accomplished extraordinary science, but there were still questions unanswered, still planets undiscovered. The engineering team refused to give up. The solution was elegant. Kepler would observe along the ecliptic plane, the plane of Earth's orbit around the Sun. By orienting perpendicular to the Sun's radiation, the spacecraft could balance the pressure of sunlight with its remaining reaction wheels and thrusters, achieving sufficient stability to detect transiting planets. K2 was never meant to match Kepler's original precision. The pointing stability just wasn't as good, but it was good enough. And by observing different fields every 80 days, we could survey far more of the sky than the original mission. Each field contained different types of stars, young clusters, old populations, bright stars ideal for follow-up. K2 became a discovery machine in its own right. From 2014 through 2018, K2 observed 19 campaigns, monitoring over 500,000 stars and discovering more than 500 confirmed planets. Among these was K2-156b, discovered during Campaign 4 in early 2015. K2 Campaign 4 ran from February 7th to April 23rd, 2015, observing a field in the direction of the constellation Aquarius. Among the approximately 16,000 stars monitored was EPIC 2-113-57309, later designated K2-156. K2 data arrives as light curves, measurements of stellar brightness taken every 30 minutes over the 80-day campaign. Automated algorithms search these light curves for periodic dips characteristic of transiting planets. When we find a promising signal, we call it candidate. K2-156b was flagged as a candidate because of regular, repeating transits every 4.8 days. But a dimming signal alone doesn't confirm a planet. False positives abound. Eclipsing binary stars, background eclipsing systems, instrumental artifacts. Every candidate requires careful vetting and, ideally, follow-up observations to confirm its planetary nature. The vetting process is meticulous. Astronomers check for secondary eclipses, analyze the shape of the transit, examine the star for stellar companions that might mimic a planetary signal, and search archival data for prior observations. For K2-156b, the transit signal passed initial vetting. The depth was consistent with a planet roughly 2.5 Earth radii orbiting the star. The shape was right, smooth ingress and egress. U-shaped bottom typical of a circular planet transiting a uniform stellar disk. No secondary eclipse was detected, ruling out a self-luminous companion. The signal looked planetary. Further confirmation came from statistical validation and follow-up observations. High-resolution imaging checked for nearby stars that could be blended with K2-156, which might harbor the true transiting object. Archival spectroscopy provided information about the host star's properties. By combining K2 photometry with ground-based imaging and stellar characterization, we confirm K2-156b as a genuine planet. The discovery was published in 2018 as part of a larger K2 planet catalog, adding another world to humanity's growing census of exoplanets. To understand K2-156b, we must first understand its star, a cool, relatively faint dwarf star located approximately 850 light-years from Earth. K2-156 is a typical K-dwarf, smaller and cooler than the Sun, but larger and hotter than M-dwarf red dwarfs. K-dwarfs are particularly interesting for exoplanet studies because they're common, relatively stable, and their habitable zones, where liquid water could exist, are closer in and around sun-like stars, making planets easier to detect. K2-156 relatively low mass and temperature affect the characteristics and habitability potential of any planets orbiting it. The star's habitable zone lies closer to the star than Earth's orbit around the Sun, roughly 0.3 to 0.6 AU, compared to Earth's 1 AU. From K2's transit observations and stellar characterization, we could derive several fundamental properties of K2-156b. But significant uncertainties remain. This is a world we're only beginning to understand. K2-156b falls in the fascinating radius range between super-Earths and mini-Neptunes, planets between 2 and 3 Earth radii. This is one of the most poorly understood regions of planetary parameter space because we have nothing like it in our solar system. These planets could be rocky worlds with thick atmospheres, water worlds with deep oceans, or small gas giants dominated by hydrogen and helium. One of the most important discoveries from Kepler and K2 is the radius valley, or Fulton Gap, a relative scarcity of planets between approximately 1.5 and 2.0 Earth radii, first identified by Benjamin Fulton at Caltech. The radius valley divides two populations. Below the gap, planets are predominantly rocky super-Earths with thin atmospheres or no atmospheres. Above the gap, planets are mini-Neptunes with substantial hydrogen-helium envelopes. The gap exists because planets that form with H/E atmospheres either retain them and stay above the gap, or lose them through atmospheric escape and drop below the gap, leaving a rocky core behind. K2-156b, with a radius around 2.4 Earth radii, sits above the radius valley. This suggests it likely has a significant volatile component, either a thick atmosphere of hydrogen and helium or substantial water/ice layers, or both. But without mass measurements, we cannot determine its density, and without density, composition remains uncertain. To determine K2-156b's composition, astronomers need to measure its mass using the radial velocity method, detecting the gravitational tug the planet exerts on its star. Radial velocity measurements are challenging for K2-156b. The star is relatively faint with an apparent magnitude around 13.5, requiring larger telescopes and longer integration times. The planet's mass is probably modest, perhaps 5 to 15 Earth masses, producing a radial velocity signal of only a few meters per second. And K-dwarf stars can be magnetically active, with star spots and stellar oscillations that mimic or mask planetary signals. As of current knowledge, published radial velocity measurements for K2-156b are limited or not yet available in the literature. This is common for fainter K2 discoveries. Follow-up observations take time, and many planets await characterization. There's a queue of K2 planets awaiting mass measurements. We prioritize based on scientific interest, feasibility, and telescope availability. K2-156b is a good candidate. Its size places it in an interesting regime, and understanding planets in this range is crucial for broader population studies. K2-156b orbits close to its star. At 0.058 AU, it receives approximately 15 to 20 times more radiation than Earth receives from the Sun. This places it well outside the habitable zone. Based on the orbital distance and stellar luminosity, we estimate an equilibrium temperature around 900 Kelvin. That's roughly 630 degrees Celsius, about the temperature of molten lead. This is too hot for liquid water on any surface. However, if the planet has a substantial atmosphere, we could study its composition using transmission spectroscopy. What might K2-156b's atmosphere contain? The answer depends critically on its composition. If K2-156b is a mini Neptune, low density, H/E dominated. Primary atmosphere of hydrogen and helium. Possible water vapor, methane, ammonia at depth. Potentially extended atmosphere suitable for transmission spectroscopy. Temperature structure influenced by greenhouse effect and atmospheric circulation. If K2-156b is a water world, moderate density, volatile rich. Thick steam atmosphere overlying deep water oceans. High-pressure water/ice layers below. Chemical equilibrium dominated by H2O, with possible CO2, N2. Potentially interesting chemistry at steam-ocean interface. If K2-156b is a rocky super-Earth, high density, minimal atmosphere. Thin or no atmosphere, possibly stripped by stellar radiation. Surface likely molten or partially molten given the temperature. Possible volcanic outgassing creating transient atmosphere. Limited potential for atmospheric detection. Without mass and density measurements, we're working with broad possibilities. That's the challenge and excitement of exoplanet science. We're piecing together a puzzle with limited information, using every technique available. K2-156b was discovered through transit photometry, the same technique that has found most known exoplanets. The method is conceptually simple but requires extraordinary precision. When K2-156b passes between us and its star, it blocks approximately 0.3% of the star's light, 3 parts in 1,000. That might sound like a lot, but detecting such a small signal requires measuring stellar brightness to better than 0.1% precision, correcting for instrumental noise, removing stellar variability, and confirming the signal repeats with a regular period. K2's photometric precision, while not as good as Kepler's original mission due to pointing instabilities, was still sufficient to detect planets. Each 30-minute measurement captured an image containing thousands of stars, with sophisticated algorithms extracting light curves for individual targets. The transit light curve reveals transit depth, how much light is blocked planet's radius relative to the star. Transit duration, how long the transit lasts, orbital speed, and planet's path across the star. Transit period, time between transits, orbital period. Transit shape, ingress/egress characteristics, limb darkening effects, and planet's path. Transit timing, precise timing of each transit, potential variations indicating other planets. From K2-156b's transit, we know its radius with reasonable confidence, about 2.4 Earth radii, with perhaps 15 to 20% uncertainty. We know its orbital period precisely, 4.820 days, accurate to within seconds. We know it transits centrally across the star's disk based on the transit duration. These are fundamental properties derived from a 0.3% dip in brightness repeated 3 or 4 times over 80 days of observation. K2's observational mode presented unique challenges compared to the original Kepler mission. The spacecraft drifted slowly over the course of each day due to imperfect balancing of solar pressure and thruster firings. This drift caused stellar images to move across the CCD detector, changing the instrument's sensitivity. We developed sophisticated software, the K2 pipeline, to correct for these systematic effects, measuring the telescope's drift and removing its influence on the light curves. Despite these challenges, K2 achieved remarkable precision, often better than 100 parts per million for bright stars, sufficient to detect Earth-sized planets and characterize larger planets like K2-156b. K2-156b is one of over 500 confirmed planets discovered by the K2 mission. Together, these planets transformed our understanding of planetary systems. K2 surveyed a diverse stellar population, young stars and open clusters, evolved red giants, white dwarfs, even binary stars. We found planets we never could have detected with the original Kepler mission. We characterized planets around bright stars suitable for atmospheric studies. We filled in gaps in our knowledge of how planets form, migrate, and evolve around different stellar types. Key K2 discoveries. K2-18b, a subneptune with detected water vapor in its atmosphere, orbiting in the habitable zone. K2-33b, one of the youngest known hot Jupiters, revealing planet migration timescales. K2-138 system, a system of 6 subneptunes in near-resonant orbits. TRAPPIST-1 planets. K2 observations refine parameters for this famous 7-planet system. HIP-41-378 system, 5 planets including rare long-period subneptunes. K2-156b adds to this legacy. While not the most extreme or unusual K2 planet, it represents the bulk of K2's discoveries, moderately sized planets on short orbits around common stars. Understanding these planets is essential for understanding planetary populations as a whole. Planets like K2-156b, subneptunes with radii between 2 and 4 Earth radii, are the most common type of planet detected by transit surveys. Yet they remain among the most mysterious. Subneptunes don't exist in our solar system, so we have no local examples to study up close. Their compositions are diverse. Some are probably rock-dominated with thick atmospheres. Others are probably ice/water-dominated. Still others might be primarily gaseous. Understanding this diversity is crucial because subneptunes are the most common planetary outcome. If we want to understand how planets form and what determines their final properties, we need to understand subneptunes. Formation theories suggest several pathways. In situ formation with gas capture. Planet forms at its current location, accretes a modest H/E envelope from the protoplanetary disk. Formation beyond the ice line with migration. Planet forms in the cold outer disk where water ice is abundant, accretes volatiles, then migrates inward. Giant planet core. Planet begins forming as a gas giant, but doesn't accrete enough gas before the disk disperses, leaving a failed Jupiter. Photoevaporation remnant. Planet forms as a larger mini-Neptune, but loses atmospheric mass to stellar radiation, leaving a smaller remnant. K2-156b's properties. Its radius, orbital period, host star type provide one data point in a vast parameter space. Each additional data point helps us test these theories. Eventually, when we've characterized hundreds or thousands of subneptunes, patterns will emerge that reveal the dominant formation and evolution processes. K2-156b is too hot to be habitable. Its equilibrium temperature of 900 Kelvin precludes liquid water and likely creates an inhospitable environment for any chemistry resembling Earth life. But studying planets like K2-156b is still essential for the search for life. Every planet we characterize teaches us about atmospheric chemistry, planetary formation, the effects of stellar radiation. When we finally observe a truly Earth-like planet, rocky, temperate, orbiting in the habitable zone, we'll need to interpret complex spectra, distinguish biological from geological signals, understand atmospheric processes. The techniques and knowledge we develop studying planets like K2-156b will be directly applicable. Moreover, the K2-156 system might contain additional planets. If other worlds orbit farther from the star, in cooler regions, they could potentially be habitable. Transit timing variations, additional transits in K2 data, or radial velocity studies might reveal these hidden companions. Multi-planet systems are common. Many K2 discoveries turn out to be multi-planet systems when we looked closely. K2-156b might have siblings, perhaps smaller planets on shorter orbits, or larger planets on longer orbits. Each additional planet gives us context for understanding the system's formation and evolution. K2-156b's characterization is incomplete. Future observations will refine our understanding and perhaps reveal surprises. Planned and potential observations. Radial velocity measurements. Using precision spectrographs like HARPS-N, or espresso to measure K2-156b's mass, determine its density, and constrain its composition. Transit spectroscopy. If K2-156b has an extended atmosphere, likely if it's a mini-Neptune, observations during transit with JWST or future facilities could detect atmospheric species like H2O, CH4, or clouds. Phase curve photometry. Monitoring K2-156b's brightness as it orbits could reveal heat redistribution between day and night sides, constraining atmospheric circulation. Additional planet searches. High-cadence photometry or radial velocity campaigns could detect additional planets in the system. High-resolution imaging. Adaptive optics imaging could search for stellar companions that might influence the system's architecture. K2-156b is a good target for follow-up because the star is bright enough for detailed studies. The planet is large enough that atmospheric characterization is feasible, and the short orbital period means we can observe multiple transits relatively quickly. As next-generation instruments come online, I expect K2-156b will be revisited. K2's mission ended in October 2018 when the spacecraft ran out of fuel. But the search for planets continues with new missions building on Kepler and K2's legacy. Transiting Exoplanet Survey Satellite, or TESS. Launched in 2018, TESS has surveyed most of the sky, finding planets around the brightest nearby stars, ideal targets for characterization. Planetary transits and oscillations of stars, or PLATO. European mission planned for launch in 2026 will monitor 1 million stars for 4 years, searching for temperate planets around Sun-like stars. Atmospheric Remote Sensing Infrared Exoplanet Large Survey, or ARIEL. European mission planned for 2029 will study atmospheres of known exoplanets, characterizing their composition and structure. Roman Space Telescope. NASA mission launching in the late 2020s will use microlensing and direct imaging to find and characterize planets. Habitable Worlds Observatory. Proposed NASA flagship mission for the 2040s, designed to directly image and characterize Earth-like planets in habitable zones. Each generation of missions answers some questions and raises new ones. Kepler asked, "Are planets common?" The answer is yes. K2 asked, "What types of planets exist around different stars?" We found tremendous diversity. Now we're asking, what are these planets made of? Do any have conditions suitable for life? The next generation will tell us. K2-156b orbits 850 light-years away, impossibly distant by human standards. The light we detect today left the star before the Renaissance, before the printing press, before the Crusades. When Kepler observed K2-156 in 2015, it captured photons that began their journey across space when English monks were illuminating manuscripts in candlelit scriptoria. We will never visit K2-156b. No spacecraft we can conceive would survive this centuries-long journey. No telescope will ever resolve the planet as more than a dot, if that. Everything we know comes from that 0.3%, dimming repeated a handful of times over 80 days. And yet, we know it. We know its size, its orbit, its temperature. We know it circles an orange sun in a cosmic dance that has continued for billions of years. We know it is real. Every exoplanet discovery is a profound act of exploration. We're reaching beyond our solar system, cataloging worlds, learning their properties. Each one expands our cosmic census, teaches us about planetary diversity, brings us closer to understanding our place in the universe. For all we've learned, fundamental questions about K2-156b remain. What is its composition? Rocky super-Earth? Water world? Mini-Neptune? The answer awaits mass measurements. Does it have an atmosphere? If so, what molecules does it contain? Can we detect them with current or near-future instruments? How did it form? Did it form in place or migrate inward? Did it lose mass over time or accrete it? Are there other planets in the system? Additional worlds might orbit K2-156, awaiting detection. What does it teach us about planetary populations? How do planets like K2-156b fit into the broader picture of planet formation and evolution? These unanswered questions aren't failures, they're opportunities. They drive future observations, motivate new missions, inspire young scientists. K2-156b is a mystery to solve, a puzzle piece in the grand picture of planetary systems. Somewhere in the constellation Aquarius, too faint for any eye to see, shines K2-156. Every 4.82 days, a world larger than Earth completes another orbit, passing between the star and our line of sight, dimming the starlight by 3 parts in 1,000. Kepler is gone now, its fuel exhausted, its mission complete. The spacecraft drifts in orbit around the Sun, a silent monument to human curiosity and ingenuity. But its legacy lives on in the thousands of planets it discovered, worlds that redefined our understanding of the cosmos. K2-156b is one planet among thousands. Not the hottest, not the largest, not the most Earth-like, not the most unusual, but it represents something essential. The continuation of exploration, the expansion of knowledge, the methodical cataloging of worlds that orbit other suns. Each discovery brings us closer to answering the profound questions. How common are planets? What types exist? How do they form? And ultimately, are we alone? K2-156b doesn't answer these questions on its own, but it contributes to the answer. It's one data point in a dataset of thousands, one piece in a puzzle that spans the galaxy. Someday, perhaps not in our lifetimes, but maybe in the lifetimes of children being born today, we will discover a planet, perhaps around a K-dwarf like K2-156, perhaps around a star much like our Sun, where conditions are right for life. When that discovery comes, we will look back at all the planets we studied along the way. Hot Jupiters and super-Earths, mini-Neptunes and water worlds, planets of iron and planets of ice. And we will realize they were not detours or disappointments. They were the path. The wilderness of worlds is vast. The search continues, and the universe always surprises us. I hope you're ready for this next one, because it's about to get chaotic. With WASP 92b, a world between extremes. In the constellation Fornax, the furnace 1,070 light-years from Earth orbits a world caught between extremes. A planet larger than Jupiter, heated to temperatures that would vaporize lead, yet cooler than the most extreme hot Jupiters. A world where day and night exist in permanent opposition, separated by a twilight zone where conditions might, just might, be unlike anything in our solar system. This is WASP 92b, a hot Jupiter that challenges our assumptions about planetary atmospheres, a laboratory for understanding how worlds respond to intense stellar radiation, and a window into the remarkable diversity of planets that populate our galaxy. This is the story of how we found it, what we've learned, and what mysteries remain. A story of ingenuity, precision, and the relentless human drive to understand worlds beyond our own. The wide-angle search for planets, WASP, is not a single telescope, but a coordinated network of robotic observatories spanning 2 hemispheres. Since 2004, These automated systems have monitored hundreds of thousands of stars, searching for the subtle dimming that betrays a planet crossing in front of its star. WASP's strength lies in its simplicity and efficiency. We use relatively small telescopes, just 11 centimeters in diameter, but with extremely wide fields of view. Each camera can monitor thousands of stars simultaneously. We take exposures every few minutes, all night, every clear night. Over months and years, we accumulate enough data to detect planets through the transit method. By 2015, WASP had discovered over 150 exoplanets, most of them hot Jupiters, giant planets orbiting extremely close to their stars. These planets are relatively easy to detect because they're large, they block significant starlight, and they transit frequently. But each hot Jupiter is unique, shaped by its specific stellar environment, its formation history, and the complex interplay of atmospheric physics and chemistry. WASP 92 caught our attention during the analysis of survey data spanning multiple observing seasons. The star showed regular, periodic dimming every 2.17 days, classic transit behavior. The depth of the dimming, about 1.5%, suggested a large planet, roughly Jupiter-sized. The regularity confirmed it wasn't instrumental noise or stellar variability. We had a candidate, but detection is only the beginning. Every candidate must be confirmed through follow-up observations using larger telescopes and precise spectroscopy. False positives, eclipsing binary stars, background objects, blended systems, must be ruled out. We used the Corley spectrograph at La Silla Observatory in Chile to measure radial velocities, the star's motion caused by the planet's gravitational pull. The measurements confirmed the signal was genuine. WASP 92b was real, a hot Jupiter with a mass about 0.8 Jupiter masses and a radius about 1.46 Jupiter radii, orbiting every 2.17 days. The discovery was published in 2016, adding another world to humanity's growing catalog of exoplanets. But the real work, understanding what WASP 92b is, how its atmosphere behaves, what it reveals about planetary physics, was only just beginning. To understand WASP 92b, we must first understand its star, the source of energy that shapes the planet's climate, chemistry, and evolution. WASP 92 is a K-type dwarf, slightly smaller, cooler, and less luminous than our Sun. These stars are particularly interesting for exoplanet studies because they're common, stable over long timescales, and their lower luminosity means planets can orbit closer and still remain potentially interesting for study. K-dwarfs strike a balance between the abundance and stability we need for comprehensive planetary surveys. WASP 92's moderate luminosity and stable nature make it an ideal host for detailed planetary studies. The star's relative quiescence, lack of dramatic flares or variability, allows astronomers to detect subtle atmospheric features in the planet without stellar noise overwhelming the signal. WASP 92b is classified as a hot Jupiter, a gas giant planet orbiting extremely close to its star, completing one orbit in just over 2 Earth days. WASP 92b represents a common class of exoplanet, hot Jupiters that orbit in days rather than years. At 0.03 AU, the planet receives about 370 times more radiation per unit area than Jupiter receives from our Sun. This intense heating inflates the atmosphere, explaining why the planet is significantly larger than Jupiter despite having less mass. The density is remarkably low, lighter than cork, because the atmosphere is puffed up by thermal energy. WASP 92b's defining characteristic is its temperature, hot enough to melt rock, but notably cooler than ultra-hot Jupiters like WASP 33b or KLT9b. With an equilibrium temperature around 1,400 Kelvin, about 1,130 degrees Celsius, WASP 92b sits in what we call the temperate hot Jupiter regime. It's hot enough that most substances we think of as solid are vaporized, but cool enough that certain molecules can survive. This temperature range is particularly interesting because it's where we expect transitions in atmospheric chemistry, where molecular species begin to break apart, where clouds might form, where thermal inversions might or might not occur. Like all close-orbiting planets, WASP, 92b is almost certainly tidally locked. One hemisphere permanently faces the star, while the other faces eternal night. This creates dramatic day-night temperature contrasts and drives powerful atmospheric circulation. The true frontier of exoplanet science is atmospheric characterization, determining what molecules exist in a planet's atmosphere and using that information to understand the planet's composition, chemistry, and climate. WASP 92b is an excellent target for atmospheric studies. Its large size means it blocks significant starlight during transits, giving us a strong signal. Its relatively bright host star means we can collect enough photons for high-precision spectroscopy. And its moderate temperature means the atmospheric chemistry should be complex and interesting. Using transmission spectroscopy, observing the planet during transit, and analyzing how its atmosphere absorbs different wavelengths of light, astronomers have begun to decipher WASP 92b's atmospheric composition. Expected and detected atmospheric species. Hydrogen and helium, H2, the dominant atmospheric components, comprising roughly 90% and 10% by mass, respectively. Water vapor, H2O. Observations have shown evidence for water vapor in WASP 92b's atmosphere, detected through broad absorption features in the infrared. Sodium, Na, and potassium, atomic metals that create strong absorption lines in the visible spectrum. Observations show tentative detections of sodium. Carbon monoxide, CO, expected to be abundant at these temperatures. Carbon chemistry shifts from methane, CH4, at cooler temperatures to CO at hotter temperatures. Titanium oxide, TO, and vanadium oxide, VO. These molecules are critical because they can create temperature inversions by absorbing optical and UV light in the upper atmosphere. Their presence or absence on WASP 92b is still being investigated. Clouds and hazes. High-altitude hazes might obscure lower atmospheric features, a common occurrence on hot Jupiters. One of the most intriguing aspects of WASP 92b is determining whether it has a temperature inversion, a stratosphere. Temperature inversions occur when molecules like TO or VO absorb stellar radiation high in the atmosphere, heating those layers. Observations so far suggest WASP 92b might lack a strong inversion, which would distinguish it from hotter Jupiters. But the data is still somewhat ambiguous. Clouds profoundly affect what we can observe. On Earth, clouds reflect sunlight and block infrared radiation. On WASP 92b, clouds might be made of exotic materials, silicates, iron compounds, or aluminum oxide. At WASP 92b's temperature, we expect certain species to condense into cloud particles, particularly on the cooler night side or at high altitudes. These are water clouds. They're mineral clouds. Instatite, a magnesium silicate, might condense around 1,300 to 1,400 K. Corundum, aluminum oxide, condenses at slightly higher temperatures. The presence and distribution of these clouds affects atmospheric spectra significantly. Observations suggest that WASP 92b's atmosphere might have high-altitude hazes that flatten spectral features, making individual molecular signatures harder to detect. This is a common finding for hot Jupiters and presents both a challenge and an opportunity. Hazes tell us about atmospheric chemistry and dynamics. Photochemical hazes form when UV light breaks apart molecules, creating complex organic compounds or soot-like particles. Understanding haze formation helps us model how energy flows through the atmosphere and how it affects temperature structure. WASP 92B's extreme day-night temperature difference, potentially 1,000 Kelvin or more, drives powerful atmospheric winds. Our general circulation models predict that hot Jupiters develop fast equatorial jet streams, supersonic winds flowing eastward around the planet. For WASP 92b, we expect wind speeds of several kilometers per second. These winds transport heat from the intensely hot day side toward the cooler night side, partially evening out the temperature difference. The winds don't completely eliminate the day-night contrast. Phase curve observations, monitoring the planet's brightness as it orbits, reveal that the hottest point on WASP 92b is offset from the substellar point, the point directly beneath the star, shifted eastward by the winds. The offset tells us about circulation efficiency. A large offset indicates strong winds are effectively redistributing heat. For WASP 92b, preliminary observations suggest moderate redistribution, more efficient than ultra-hot Jupiters where the day side is so hot that winds can't transport heat effectively, but less efficient than cooler hot Jupiters where circulation is more uniform. Every 2.17 days, WASP 92b passes between its star and Earth, creating a transit, a temporary dimming of the star's light. This simple event, lasting about 2.5 hours, is the foundation of everything we know about the planet. The transit depth tells us the planet size. WASP 92b blocks approximately 1.5% of its star's light, which means the planet's cross-sectional area is 1.5% of the star's. From this, we calculate the planet's radius, about 1.46 Jupiter radii. The duration of the transit depends on the planet's orbital speed and its path across the star. By modeling the exact shape of a light curve, we could determine orbital inclination and check for limb darkening effects. But transits reveal more than just size. The wavelength-dependent depth, how much light is blocked at different colors, encodes information about the planet's atmosphere. During a transit, some starlight passes through the planet's atmosphere before reaching us. Different molecules absorb different wavelengths, creating a unique spectral signature. Imagine the planet as a backlit silhouette. The atmosphere around the limb is like a glowing ring. We don't see the ring directly. We see its effect on the star spectrum. Water vapor absorbs in the infrared, creating deeper transits at those wavelengths. Sodium absorbs yellow light. Clouds scatter light broadly, flattening spectral features. By comparing spectra taken during transit versus out of transit, we isolate the atmospheric contribution. For WASP 92b, transmission spectroscopy has revealed tentative signatures of water vapor and possibly sodium. But clouds or hazes complicate interpretation, muting the signals and requiring careful modeling. To measure WASP 92b's mass, astronomers use the radial velocity method, detecting the star's wobble caused by the planet's gravity. As WASP 92b orbits, it pulls on the star gravitationally. The star and planet orbit their common center of mass. For WASP 92, this causes the star to move toward and away from us at approximately 80 meters per second. By measuring the Doppler shift in the star's spectral lines over multiple orbits, we determined WASP 92b's mass, about 0.8 Jupiter masses. Combining mass and radius gives density, a crucial diagnostic. WASP 92b's density of 0.26 grams per cubic centimeter, about one-third of Jupiter's, confirms that the highly inflated hot Jupiter, its atmosphere puffed up by intense stellar heating. One of the most powerful techniques for studying hot Jupiters is phase curve photometry, monitoring the planet's brightness throughout its entire orbit. As WASP 92b orbits, we see different hemispheres. Before transit, we see mostly night side. After transit, we see mostly dayside. During secondary eclipse, when the planet passes behind the star, the day side is hidden. By measuring brightness changes, we map temperature across the planet's surface. Phase curve observations of WASP 92b reveal a day-night temperature difference of several hundred Kelvin and an eastward offset of the hottest region, signatures of atmospheric circulation that confirm theoretical models. WASP 92b is 1,070 light-years away, a distance so vast that light takes more than a millennium to traverse it. The photons we detect today began their journey before the Norman conquest of England. The challenges of studying distant exoplanets cannot be overstated. WASP 92, with an apparent magnitude of 13.2, is about 630 times fainter than the faintest stars visible to the naked eye. To detect the 1.5% transit of WASP 92b requires measuring the star's brightness to better than 0.1% precision, and doing so repeatedly over weeks or months to catch multiple transits. Then there's the scale of the signal. When astronomers study WASP 92b's atmosphere through transmission spectroscopy, they're measuring changes of a few parts in 10,000, detecting that the transit is 0.01% deeper at one wavelength compared to another. Stars are not perfect, unchanging beacons. They have spots, flares, oscillations, variability that can mimic or mask planetary signals. Star spots are like sunspots, cooler, darker regions on the stellar surface caused by magnetic activity. If a planet transits over a star spot, the transit depth changes slightly because the planet is blocking a darker region. This can introduce errors in radius measurements or create apparent variations in atmospheric spectra. We must carefully model stellar activity to extract genuine planetary signals. For WASP 92, the K-type host star is relatively quiet, making observations somewhat easier than for younger, more active stars. But stellar noise is always a consideration, requiring sophisticated data analysis techniques. Even the best instruments have limitations, sensitivity thresholds, wavelength coverage gaps, systematic errors. Ground-based observations face atmospheric interference. Water vapor in Earth's atmosphere absorbs the same wavelengths we're trying to detect from exoplanets. Space-based telescopes like Hubble and now James Webb avoid this problem, but have limited observing time and must compete with many other science priorities. Every observation of WASP 92b requires careful planning, calibration, and data reduction. These challenges drive innovation. New instruments, new techniques, new telescopes. Each generation pushes the boundaries of what's detectable, bringing planets like WASP 92b into sharper focus. The James Webb Space Telescope, launched in December 2021, is revolutionizing exoplanet atmospheric studies with unprecedented infrared sensitivity. JWST's NIRISS and NIR spec instruments can observe WASP 92b's transmission spectrum from 1 to 5 microns with exquisite precision. This wavelength range contains strong absorption features from water, carbon monoxide, methane, and other molecules. We can also observe secondary eclipses to measure thermal emission, constraining temperature structure and heat redistribution. While comprehensive JWST observations of WASP 92b may still be pending or underway, the telescope's capabilities promise to answer lingering questions. Does the planet have a temperature inversion? What is the carbon-to-oxygen ratio in its atmosphere? Are there hazes? And if so, at what altitude? How efficiently does the atmosphere transport heat? Complementing space-based observations, ground-based high-resolution spectroscopy offers unique capabilities. With instruments like Espresso or Crier's Plus on the VLT, we can detect individual absorption lines from atoms and molecules in exoplanet atmospheres. For WASP 92b, we might detect sodium, potassium, iron, or water at high spectral resolution. We can also measure Doppler shifts caused by atmospheric winds, directly observing how fast gas is moving. This provides a window into circulation that complements lower resolution studies. These observations are revealing WASP 92b's atmosphere in 3 dimensions, not just what's there, but where it is and how it moves. WASP 92b doesn't exist in isolation. It's one of hundreds of hot Jupiters, each with unique characteristics that collectively reveal how these planets form, evolve, and respond to different environments. Comparative planetology is essential. WASP 92b, with its moderate temperature and moderate inflation, sits in a regime between the coolest and hottest hot Jupiters. By comparing WASP 92b to planets like WASP 12b, hotter, more inflated, actively evaporating, and to cooler hot Jupiters with different atmospheric chemistry, we map out the transitions. Where do clouds form? Where do molecules dissociate? Where do temperature inversions appear? Each planet is a data point in parameter space. WASP 92b's position, neither the hottest nor the coolest, neither the most inflated nor the densest, makes it a valuable benchmark for understanding the population as a whole. One of the most puzzling features of hot Jupiters is atmospheric inflation, why many are significantly larger than models predict. WASP 92b is moderately inflated, larger than Jupiter despite having less mass. The canonical explanation is that stellar radiation heats the atmosphere, and somehow energy is transported deep into the planet's interior, preventing it from contracting. But the details are debated. Is it ohmic dissipation from electric currents? Kinetic energy from winds? Enhanced opacity? WASP 92b, sitting in a moderate temperature regime, helps us test these mechanisms. By measuring WASP 92b's radius precisely and understanding its atmosphere properties, astronomers can strain which inflation mechanisms are most important, knowledge applicable to understanding hot Jupiters throughout the galaxy. WASP 92b could not have formed where it orbits now. Giant planets require large amounts of material, rock, ice, and gas, available only in the cold outer regions of protoplanetary disks. WASP 92b formed several astronomical units from its star, likely beyond the ice line where water and other volatiles were frozen. It then migrated inward, either through disk migration, gravitational interactions with the protoplanetary disk, or through dynamical scattering, encounters with other planets that ejected siblings and sent WASP 92b inward. The planet's nearly circular orbit suggests it migrated smoothly through disk interactions rather than through violent dynamical scattering. Tidal forces from the star have since circularized any residual eccentricity and locked the planet's rotation to its orbit. WASP 92b will never host life. At 1,400 Kelvin, water exists only as vapor, if at all. No organic chemistry remotely resembling biology could proceed. The planet is utterly hostile to life as we know it. Yet studying WASP 92b advances the search for habitable worlds. Every planet we characterize teaches us about atmospheres, how they form, how they respond to stellar radiation, what molecules we can detect, and how. The techniques we develop for hot Jupiters, transmission spectroscopy, phase curves, high-resolution Doppler spectroscopy, will be directly applicable when we study temperate, rocky planets. WASP 92b is a laboratory for perfecting our methods. Moreover, understanding hot Jupiters helps us understand planetary system architecture. Do systems with hot Jupiters also contain smaller, potentially habitable planets? How does the presence of a migrating giant affect the formation and survival of rocky worlds? WASP 92b's existence tells us about the WASP 92 systems history and constraints where other planets might exist. Somewhere in the constellation Fornax, 1,070 light-years from Earth, WASP, 92b continues its eternal orbit. Every 2.17 days, every 52 hours, it completes another circuit around its orange star. The day side bakes under relentless radiation. The night side cools into relative darkness. Between them, the twilight zone churns with supersonic winds and exotic clouds. No human will ever visit WASP 92b. The distances are too vast, the environment too hostile. But we can study it. We can understand it. We can marvel at it. A world utterly unlike Earth, yet governed by the same physical laws, shaped by the same forces that formed our own planet. WASP 92b represents both the diversity and the commonality of planetary systems. It's extreme by Earth standards, larger, hotter, faster orbiting. Yet it's typical for a hot Jupiter, one of hundreds with similar properties. This duality, unique yet representative, makes it invaluable for scientific study. With every observation, we learn more. We refine our atmospheric models. We test our theories of planetary formation. We develop new techniques that will eventually reveal Earth-like worlds around other stars. And perhaps most importantly, planets like WASP 92b expand our sense of what's possible. They remind us that the universe is richer, stranger, more varied than our imaginations. They inspire wonder, the same wonder that drove ancient peoples to name the constellations, that motivated Galileo to point his telescope at Jupiter's moons, that compels modern astronomers to spend cold nights collecting photons from distant stars. This is WASP 92b, a hot Jupiter, a world of extremes, a laboratory for understanding planetary atmospheres, a stepping stone in humanity's quest to find other worlds, and perhaps, someday, another Earth. The search continues. The mysteries deepen, and the universe always surprises us. Next, let's dive into the Earth-like world of LHS 3859b, the Red Star's companion. Just 57 light-years from Earth, a cosmic stone's throw in galactic terms, orbits a star so faint you'd need a telescope to see it. LHS 3859, a red dwarf no larger than 1/3 the Sun's diameter, burning with barely 2% of our Sun's luminosity. For billions of years, this star went unnoticed by humanity, cataloged only as an entry in astronomical surveys. Until 2019, when astronomers detected something extraordinary, a planet. Not a gas giant like Jupiter, but a rocky super-Earth, larger than our world, but potentially similar in composition. This is LHS 3859b, a world that might, just might, teach us whether rocky planets around the galaxy's most common stars can harbor the conditions necessary for life. For most of human history, we've focused on stars like our Sun, bright, yellow, massive enough to fuse hydrogen efficiently for billions of years. But the galaxy's true masters are far more modest. Red dwarfs, M-type stars that comprise roughly 75% of all stars in the Milky Way. Red dwarfs are the ultimate survivors of the cosmos. They're so small and cool that they burn hydrogen incredibly slowly. While the Sun will live for about 10 billion years, a typical red dwarf might shine for 100 billion years or more, longer than the current age of the universe. If habitable planets exist around these stars, life would have enormous time scales to develop. But red dwarfs present challenges. They're small, cool, and dim, which means they're habitable zones. The orbital distances where liquid water could exist are very close to the star. Planets in these zones receive intense stellar radiation, face tidal locking, and may be bombarded by flares. For decades, we debated whether red dwarfs could host habitable planets. The close orbital distances seemed problematic. planets might be tidally locked with permanent day and night sides, or they might lose their atmospheres to stellar radiation. But as we've discovered more planets around M dwarfs, we've realized that nature doesn't respect our preconceptions. These systems are diverse, complex, and potentially habitable. NASA's Transiting Exoplanets Survey Satellite, TESS, launched in 2018 with a mission to survey the entire sky, focusing on the brightest, nearest stars. Unlike Kepler, which stared at a distant patch of sky, TESS observes nearby stars that are bright enough for detailed follow-up studies. TESS is designed to find planets around our stellar neighbors, stars within 50 to 300 light-years. These are stars bright enough that we can measure their radial velocities, characterize their atmospheres, and conduct the kind of detailed studies necessary to understand planetary properties. TESS has found thousands of planet candidates, many around the most common stars in our neighborhood, red dwarfs. Among TESS's early targets was the star LHS 3859, a designation that refers to its listing in the Luton half-second catalog, a survey of stars with high proper motion. This small, faint red dwarf, located just 57 light-years away in the constellation Indus, seemed unremarkable until TESS detected a regular dimming every 2.05 days. In 2019, TESS Sector 12 observations captured light from LHS 3859 with 2-minute cadence, measuring the star's brightness every 2 minutes over 27 days. The signal was clear, a regular, repeating transit with a period of 2.05 days. The depth of the transit, approximately 0.5%, told us this was a small planet, likely rocky, probably between the size of Earth and Neptune. The regularity and shape of the transit were consistent with a genuine planetary signal rather than an eclipsing binary or instrumental artifact. But detection is just the beginning. Every candidate must be vetted, checked for false positives, validated through additional observations, and ideally confirmed through independent methods. To confirm LHS 3859b and measure its mass, astronomers turn to the radial velocity method, detecting the star's wobble caused by the planet's gravitational pull. We used the Carmenes spectrograph at Calar Alto Observatory in Spain, an instrument specifically designed for precision radial velocity measurements of red dwarfs. M dwarfs are challenging targets because they're faint and their spectra contain many molecular absorption lines. But Carmenes operates in the near-infrared, where M dwarfs are brightest. The radial velocity measurements confirmed the planet's existence and revealed its mass, approximately 1.9 Earth masses. Combined with the radius derived from transit observations, approximately 1.35 Earth radii, astronomers could calculate the planet's density, approximately 6.0 grams per cubic centimeter, significantly higher than Earth's 5.5 g/cm superscript 3. The high density suggests LHS 3859b is likely a rocky planet with an iron-rich core, similar in composition to Mercury or Earth. It's not a mini-Neptune with a thick gaseous envelope. It's a genuine super-Earth, a scaled-up version of rocky planets like our own. LHS 3859 is representative of the most common stellar type in the galaxy. It's cooler than the Sun by more than 2,000 Kelvin, which means it emits most of its energy in the infrared rather than visible light. From a planet orbiting LHS 3859, the star would appear deep orange or red, almost ember-like, and would look about 3 times larger in angular size than our Sun appears from Earth, compensating somewhat for its much lower luminosity. LHS 3859's low luminosity means its habitable zone, where liquid water could exist, is very close to the star, roughly 0.05 to 0.12 AU, about 7.5 to 18 million kilometers. For comparison, Mercury orbits the Sun at 0.39 AU and Earth at 1 AU. LHS 3859b is substantially larger and more massive than Earth, but it's still in the rocky planet regime. The radius is below the critical threshold, around 1.5 to 1.6 Earth radii, where planets transition from rocky to gaseous. This planet likely has a solid surface, though what that surface is like depends critically on whether it has an atmosphere. At 0.026 AU, LHS 3859b orbits more than 38 times closer to its star than Earth orbits the Sun. But because LHS 3859 is so much dimmer than the Sun, the planet receives only about 5.4 times more radiation than Earth receives, comparable to Venus in our solar system. The equilibrium temperature, the temperature the planet would reach if it perfectly absorbed and redistributed stellar radiation, is estimated around 500 to 600 Kelvin, depending on assumptions about the planet's albedo and heat redistribution. That's roughly 230 to 330 degrees Celsius. Too hot for liquid water on the surface, well outside the habitable zone. The planet is almost certainly tidally locked. One hemisphere permanently faces the star, the other faces eternal night. This creates extreme temperature gradients between the day side, potentially 700 to 800 K, and night side, potentially 200 to 300 K. LHS 3859b orbits well inside its star's habitable zone. At its current location, surface water could not exist in liquid form. The planet is too hot, too irradiated, too hostile for Earth-like life. But this doesn't mean the planet is scientifically uninteresting, quite the opposite. LHS 3859b is exactly the kind of planet we need to study to understand rocky planet evolution around M dwarfs. It's close enough that we can potentially characterize its atmosphere. It's dense enough that it's likely rocky, and it's hot enough that atmospheric processes, chemistry, circulation, potential atmospheric loss, should be active and detectable. Every rocky planet we characterize, regardless of habitability, teaches us about the diversity of terrestrial worlds. Does LHS 3859b have an atmosphere? If so, what is it made of? These questions are central to understanding the planet's nature. There are several possibilities. The planet might have lost any primordial atmosphere due to intense stellar radiation and stellar wind, especially during the star's active youth when M dwarfs are known to be more violent. In that case, LHS 3859b would be a barren, rocky world with no atmosphere, similar to Mercury in our system. Alternatively, the planet might have retained or outgassed a secondary atmosphere. Volcanic gases like carbon dioxide, sulfur dioxide, or water vapor. Given the temperature, water vapor would dominate the atmosphere, potentially creating a thick steam atmosphere. Or the planet might have an atmosphere dominated by heavier gases that are harder to strip away, a Venus-like scenario with thick CO2. Atmospheric scenarios. Scenario 1. No atmosphere, airless rocky world. Stellar wind and radiation stripped away primordial atmosphere. Surface directly exposed, tidally locked with extreme day-night temperature contrast. Similar to Mercury, but larger and denser. Detectable through flat transmission spectrum. Scenario 2. Thin secondary atmosphere. Volcanic outgassing produces CO2, SO2, H2O vapor. Moderate greenhouse effect. Some atmospheric circulation redistributing heat. Potentially detectable molecular features in transmission spectroscopy. Scenario 3. Thick steam atmosphere. High temperatures vaporize surface water, if present. Dense H2O-dominated atmosphere with strong greenhouse effect. Possibly ocean beneath thick atmosphere at high pressures. Strong water vapor features in transmission spectrum. Scenario 4. Venus-like atmosphere. Runaway greenhouse effect with thick CO2 atmosphere. Surface temperatures exceeding 700 K. Highly reflective clouds, possibly sulfuric acid. Strong CO2 absorption features. Determining which scenario is correct requires observations, transmission spectroscopy during transits, thermal emission measurements, detailed atmospheric modeling. These observations are now possible with the James Webb Space Telescope and other advanced instruments. Tidal locking is almost certain for planets orbiting so close to their stars. Over millions of years, tidal forces synchronize the planet's rotation period with its orbital period, resulting in permanent day and night hemispheres. Tidal locking fundamentally changes a planet's climate. On the day side, the star never sets. It hangs at a fixed point in the sky, baking the surface continuously. On the night side, the star never rises. It's perpetual twilight or darkness, with temperatures potentially plunging as heat radiates into space. The terminator, the boundary between day and night, becomes the most interesting region, where conditions might be moderate. If LHS 3859b has a substantial atmosphere, winds would transport heat from the scorching day side to the freezing night side, moderating temperatures. But without an atmosphere, the temperature extremes would be severe. Tests discovered LHS 3859b using the transit method, monitoring the star's brightness and detecting the periodic dimming caused by the planet crossing in front of the star. For LHS 3859, the transit lasts about 1.5 hours out of the planet's 2.05-day orbital period. During that time, the planet blocks approximately 0.5% of the star's light, a small signal, but TESS is precise enough to detect it. The depth tells us the planet's size relative to the star. The duration tells us about the orbital speed and geometry. The period tells us how long the planet's year is. TESS observed multiple transits of LHS 3859b during Sector 12, allowing astronomers to measure the orbital period with extreme precision, 2.05106 days, accurate to within seconds. To measure LHS 3859b's mass, astronomers used the Carmenes instrument, a high-resolution spectrograph designed specifically for M-dwarf radial velocity studies. As LHS 3859b orbits, it gravitationally tugs on its star, causing the star to move in a small orbit around the system's center of mass. This motion causes Doppler shifts in the star's spectrum. The light shifts to bluer wavelengths when the star moves toward us, and to redder wavelengths when it moves away. For LHS 3859b, the radial velocity amplitude is approximately 2.5 meters per second, about walking speed. Measuring velocities of a few meters per second requires extraordinary precision. Carmenes achieves this by stabilizing the spectrograph thermally and measuring the spectrum against a precise wavelength reference, a laser frequency comb or a gas absorption cell. M-dwarfs present unique challenges and advantages for radial velocity. They're faint, requiring longer exposures. They have many molecular absorption lines, which can be good for precision but also make the analysis complex. However, M-dwarfs are most luminous in the near-infrared, where Carmenes operates, giving us an advantage. And because M-dwarfs are low mass, the radial velocity signal for a given planet mass is larger than for a Sun-like star. By combining transit observations, which give radius, with radial velocity measurements, which give mass, astronomers derive density, a key diagnostic for determining composition. LHS 3859b's density of 6.0 grams per cubic centimeter is higher than Earth's 5.5, suggesting a planet with a relatively large iron core, perhaps 30 to 40% of the planet's radius, compared to Earth's core at about 25%. This high metal content might result from formation closer to the star where temperatures were higher, preventing volatile ices from condensing, or from collisional stripping of the outer layers during the planet's formation. The density confirms LHS 3859b is not a mini-Neptune or water world. It's a genuine rocky super-Earth, likely composed primarily of iron and silicates. One of the most exciting prospects for LHS 3859b is atmospheric characterization using the James Webb Space Telescope and other next-generation instruments. LHS 3859b is an excellent target for transmission spectroscopy. The planet is relatively large, producing a deeper transit than Earth-sized planets. The host star, while faint in visible light, is brighter in the infrared where JWST operates, and the star is quiet enough that stellar activity won't overwhelm planetary signals. We can observe multiple transits and measure the spectrum with unprecedented precision. As of the available data, comprehensive JWST observations of LHS 3859b may still be pending or in progress, but the potential is enormous. What JWST could reveal: presence or absence of atmosphere. A flat spectrum, transit depth independent of wavelength, would indicate no atmosphere. Wavelength-dependent features would confirm atmospheric absorption. Molecular composition: water vapor, carbon dioxide, methane, sulfur dioxide, or other molecules would create unique spectral signatures. Temperature structure: secondary eclipse observations, when the planet passes behind the star, would measure thermal emission, constraining dayside temperature and heat redistribution. Cloud properties: clouds would mute spectral features and potentially create wavelength-dependent scattering signatures. Even a null detection, confirming the planet has no atmosphere, would be scientifically valuable. It would tell us that rocky planets this close to M dwarfs cannot retain atmospheres, constraining atmospheric escape models and informing the search for habitable planets at greater distances. LHS 3859b is one of hundreds of planets discovered around red dwarfs. Together, these discoveries are revealing patterns about how planets form, evolve, and potentially harbor life around the galaxy's most common stars. We're finding that M dwarfs frequently host small planets, super-Earths, and sub-Neptunes. The occurrence rate of rocky planets around M dwarfs appears to be even higher than around Sun-like stars. On average, every M dwarf might host one or more planets in size, ranges relevant for habitability. Given that M dwarfs comprise 75% of all stars, this means the majority of potentially habitable planets in the galaxy might orbit red dwarfs. Each discovery adds to our understanding. LHS 3859b, though too hot for habitability, helps us understand atmospheric retention, surface composition, and the effects of stellar radiation on rocky worlds. Knowledge directly applicable to assessing habitability of cooler planets. Ground-based facilities continue to study LHS 3859b, refining measurements and searching for additional planets in the system. We're conducting extended radial velocity monitoring to improve the mass measurement precision and search for additional planets. Many systems host multiple planets, and LHS 3859 might have siblings, perhaps a planet farther out, in or near the habitable zone. Transit timing variations, slight deviations from perfectly periodic transits, could also reveal unseen planets through gravitational interactions. High-resolution imaging using adaptive optics checks for stellar companions, binary stars that could affect the system's dynamics or complicate interpretations. Photometric monitoring searches for stellar flares or spot activity that could influence atmospheric studies. LHS 3859b's high density and close orbit provide clues about rocky planet formation around red dwarfs. Forming rocky planets close to M dwarfs is challenging. The protoplanetary disk in these inner regions has little mass. Planets must grow quickly before the disk dissipates. LHS 3859b's high density and iron-rich composition suggest it formed from material depleted in volatiles, either because temperatures were high enough to vaporize ices or because collisional processes stripped away lighter materials. Alternatively, LHS 3859b might have formed farther out and migrated inward through interactions with the protoplanetary disk or other planets. Migration could explain the circular orbit and position close to the star. One of the critical questions for M-dwarf planets is atmospheric retention. Can planets this close to active stars maintain atmospheres over billions of years? M-dwarfs, especially when young, can be violent, producing frequent flares and strong stellar winds that can strip away planetary atmospheres. High-energy UV and X-ray radiation can photoevaporate atmospheres, especially for low-mass planets with weaker gravity. LHS 3859b, with its high density and relatively strong gravity, is better positioned to retain an atmosphere than lower-density planets, but it's still uncertain whether it has one. Understanding atmospheric escape on LHS 3859b informs habitability assessments for planets in M-dwarf habitable zones. If planets like LHS 3859b, denser and more massive than Earth, struggle to retain atmospheres, what does that mean for smaller planets farther out? LHS 3859b will never host life. Its surface temperature is too high, its proximity to the star too extreme. But studying it is essential for the search for life elsewhere. Every rocky planet we characterize teaches us about planetary diversity, atmospheric chemistry, and the effects of stellar environments. LHS 3859b is a laboratory for understanding how radiation affects rocky worlds around M-dwarfs. We develop techniques, test models, and refine our understanding. When we finally observe a truly habitable planet around an M-dwarf, rocky, temperate, with a stable atmosphere, we'll need every lesson learned from planets like this one. Moreover, the techniques developed for LHS 3859b, high-precision transit photometry, infrared spectroscopy, radial velocity measurements, are directly applicable to studying potentially habitable worlds. Just 57 light-years away, a distance light travels in the span of a human lifetime, orbits LHS 3859b. Every 2.05 days, the planet completes another circuit around its red dwarf star. One hemisphere bakes under constant starlight. The other freezes in endless night. Between them, the terminator, the boundary of twilight, might be the only region with temperatures moderate enough for complex chemistry. We will likely never visit LHS 3859b, even traveling at 1% the speed of light. Far beyond our current capabilities, the journey would take 5,700 years. But we can study it. We can understand it. We can learn from it. LHS 3859b is not alone. It's one of thousands of known exoplanets, one of hundreds around red dwarfs, one of dozens of rocky super-Earths. Each discovery refines our cosmic census. Each characterization teaches us something new. Somewhere in this galaxy, perhaps orbiting an M-dwarf not so different from LHS 3859, perhaps at a distance just a bit farther out in the temperate zone where water could be liquid, there might be a world where life has taken hold. When we find that world, we will draw on everything we've learned from planets like LHS 3859b. Every technique, every model, every hard-won piece of understanding will guide our interpretation. This is LHS 3859b, a super-Earth, a rocky world, a planet too hot for life but perfect for learning. A stepping stone in humanity's journey to answer the oldest question, are we alone? The search continues, the discoveries multiply, and the universe, always, has more to teach us. This next planet on our list is very special. Let's peek through the fog and look at WASP 39b, the cloud world, and the dawn of atmospheric science. On July 12, 2022, humanity witnessed a revolution. The James Webb Space Telescope, the most powerful observatory ever launched, revealed its first observations of an exoplanet's atmosphere. Not an image of clouds or continents, but something more profound, a detailed chemical fingerprint showing what molecules exist in the atmosphere of a world 700 light-years away. The planet was WASP 39b, a gas giant larger than Saturn, orbiting closer to its star than Mercury orbits our Sun. And in its atmosphere, JWST detected water vapor, carbon dioxide, carbon monoxide, sodium, potassium, and, for the first time definitively in an exoplanet, sulfur dioxide, created by photochemistry high in the atmosphere. This wasn't just data. This was a Rosetta Stone for understanding alien worlds, proof that we can analyze the atmospheres of planets orbiting distant stars with unprecedented detail, opening a new era in the search for life beyond Earth. Our story begins in 2011, when a wide-angle search for planets, WASP, was systematically monitoring hundreds of thousands of stars, searching for the periodic dimming that betrays a transiting planet. WASP 39, cataloged as 1 SWASP J064515.23-034424.3, was a relatively bright star, magnitude 11.9, making it visible to modest telescopes. Over multiple observing seasons, we detected regular transits every 4.05 days. The depth, about 2.5%, indicated a large planet, roughly Saturn-sized. The regularity confirmed it wasn't an artifact or eclipsing binary. We had a genuine hot Saturn. Follow-up radial velocity measurements using the Corelli spectrograph confirmed the planet's mass, approximately 0.28 Jupiter masses, or roughly the same as Saturn. Combined with the radius derived from transits, 1.27 Jupiter radii, larger than Saturn, astronomers calculated a remarkably low density, just 0.19 grams per cubic centimeter, about 1/5 of Saturn's density. WASP 39b is what we call an inflated hot Saturn, a gas giant with mass similar to Saturn, but a radius significantly larger, resulting in very low density. This inflation is caused by intense stellar heating. The planet orbits at just 0.0486 AU, only 7.3 million kilometers from its star, receiving enormous amounts of radiation that prevents the atmosphere from contracting. WASP 39 is an excellent host star for atmospheric studies. It's relatively bright, quiet, not prone to intense flares, and old, meaning it's settled in a stable behavior. These characteristics make it easier to detect subtle atmospheric features in the planet's spectrum without stellar noise overwhelming the signal. Even before JWST, astronomers recognized WASP 39b as a prime target for atmospheric characterization. The planet's large size, puffy atmosphere, and bright host star made it ideal for transmission spectroscopy. In 2018, we published Hubble observations of WASP 39b that revealed strong water vapor absorption features across multiple wavelengths, from optical through near-infrared. This was significant because water vapor is a key molecule for understanding atmospheric composition, temperature structure, and chemistry. We also detected evidence for clouds or hazes at high altitudes. These early observations hinted at WASP 39b's potential, a world with a complex atmosphere, accessible to detailed study, waiting for more powerful instruments to reveal its secrets. The James Webb Space Telescope, a $10 billion observatory decades in the making, launched on Christmas Day, 2021. With a 6.5-meter gold-coated mirror and instruments optimized for infrared wavelengths, JWST promised to revolutionize exoplanet atmospheric studies. JWST was designed to do what previous telescopes couldn't: observe exoplanet atmospheres with unprecedented sensitivity and wavelength coverage. For a planet like WASP 39b, JWST could detect not just water vapor, but dozens of molecular species across a wide infrared range. It could measure abundances, constrain temperature profiles, reveal atmospheric chemistry in exquisite detail. WASP-39b was selected as one of JWST's early release science targets. Observations designed to demonstrate the telescope's capabilities and provide immediate scientific results. In July 2022, JWST observed WASP-39b using multiple instruments and observing modes. NIR spec, near-infrared spectrograph, observed transmission spectrum from 0.6 to 5.3 microns with high resolution, detecting molecular features. NIRIS, near-infrared imager and slitless spectrograph, obtained transmission spectrum from 0.6 to 2.8 microns, complementing NIR spec data. NIR-CAM, near-infrared camera, performed time series observations measuring the planet's brightness at specific wavelengths. MIRI, mid-infrared instrument, observed eclipse spectrum thermal emission from 5 to 12 microns, probing deeper atmospheric layers. This was the most comprehensive atmospheric characterization of an exoplanet ever conducted. We observed WASP-39b from multiple angles. Transmission spectroscopy during transit to probe the atmosphere's limb, eclipse spectroscopy when the planet passed behind the star to measure day-side thermal emission. We covered wavelengths that contain absorption features from water, carbon dioxide, carbon monoxide, methane, sulfur compounds, and more. The results exceeded expectations. JWST didn't just detect molecules. It measured their abundances with unprecedented precision. Molecules detected in WASP-39b's atmosphere. Water vapor, H2O. Strong absorption features throughout the spectrum. Abundance measurements suggest water vapor comprises a significant fraction of the atmosphere after hydrogen and helium. Carbon dioxide, CO2. Clear, unambiguous detection at 4.3 microns. The clearest CO2 detection in an exoplanet atmosphere at the time, confirming predictions from atmospheric models. Carbon monoxide, CO, detected at 4.6 microns, providing information about carbon chemistry and atmospheric temperature. Sulfur dioxide, SO2, the surprise discovery, detected at 8.5 microns. This was the first definitive detection of sulfur dioxide in an exoplanet atmosphere, indicating active photochemistry. Sodium, Na, and potassium, K. Atomic absorption features in the optical/near-infrared, confirming earlier ground-based and Hubble detections. Hydrogen sulfide, H2S. Tentative detection suggesting sulfur-bearing compounds are present beyond SO2. This chemical inventory tells us about the planet's formation and evolution. The carbon-to-oxygen ratio, derived from CO2, CO, and H2O abundances, suggests WASP-39b formed from planetesimals and gas that accreted beyond the water-ice line in its protoplanetary disk. The sulfur dioxide reveals ongoing photochemistry. UV light from the star is breaking apart hydrogen sulfide and other molecules, creating SO2 high in the atmosphere. The detection of sulfur dioxide was particularly groundbreaking, the first time photochemistry had been definitively observed on an exoplanet. On Earth, sulfur dioxide is produced by volcanic eruptions and industrial processes. On WASP-39b, SO2 is created when ultraviolet light from the star breaks apart hydrogen sulfide molecules. The sulfur and oxygen atoms then recombine to form sulfur dioxide. This is photochemistry, chemical reactions driven by light, and detecting it means we can study how stellar radiation affects atmospheric composition. On Earth, photochemistry creates the ozone layer that protects life from harmful radiation. Understanding photochemistry on exoplanets helps us predict which molecules might be biosignatures, signs of life, and which are purely abiotic. JWST's observations don't just reveal what's in the atmosphere. They tell us how the atmosphere is structured vertically and how it circulates globally. By analyzing the transmission spectrum at different wavelengths, we probe different atmospheric altitudes. Wavelengths where molecules absorb strongly let us see higher altitudes, where pressures are lower. Wavelengths with weaker absorption probe deeper, higher pressure layers. From this, we construct a temperature-pressure profile, essentially how temperature changes with altitude. WASP-39b's atmosphere shows evidence for a temperature inversion, a layer where temperature increases with altitude rather than decreasing. This is caused by molecules like titanium oxide, vanadium oxide, or potentially sulfur compounds absorbing stellar radiation high in the atmosphere. But there's more. The spectrum also shows evidence for clouds. Clouds mute spectral features. They make molecular absorption lines shallower because cloud particles scatter light, obscuring the gas below. WASP-39b spectrum shows some muting, but not as much as seen on some other hot Jupiters. This suggests patchy clouds or hazes at high altitudes, but not a thick, opaque cloud deck. The clouds might be composed of silicates, iron compounds, or salts that condense at these temperatures. Like all close-orbiting planets, WASP-39b is likely tidally locked. One hemisphere permanently faces the star, the other faces eternal night. Tidal locking creates extreme day-night temperature contrasts. The day side, baked by constant stellar radiation, can reach temperatures exceeding 1,100 Kelvin, over 800 degrees Celsius. The night side, receiving no direct starlight, cools to perhaps 600 to 800 Kelvin. These temperature differences drive powerful atmospheric winds, supersonic jet streams that transport heat from day to night. Eclipse observations, when WASP-39b passes behind its star and we lose its thermal emission, provide information about dayside temperature and heat redistribution efficiency. JWST's MIRI instrument observed secondary eclipse, measuring the planet's thermal emission spectrum. The brightness temperature derived from these observations is approximately 1,100 Kelvin on the day side. The spectrum shows emission features from water vapor and carbon dioxide, indicating we're seeing down to depths where these molecules emit thermal radiation. This tells us about the atmospheric temperature structure and how efficiently heat is transported. The extreme temperature difference between day and night doesn't just affect circulation, it affects chemistry. On the hot day side, molecules like water can remain in vapor form. On the cooler night side, water might condense into clouds. Similarly, certain metal compounds that are gaseous on the day side could condense on the night side. This creates a day-night chemical asymmetry. Winds transport gas between these regions, creating a dynamic, evolving chemical environment. This chemical cycling, molecules evaporating on the day side, condensing on the night side, and being transported by winds, creates weather patterns unlike anything in our solar system. The atmospheric composition of WASP-39b provides clues about where and how the planet formed. The enrichment of heavy elements, carbon, oxygen, sulfur, relative to hydrogen, tells us about the planet's formation history. WASP-39b's atmosphere shows significant water vapor and carbon dioxide, suggesting it formed from material enriched in ices and rock. The carbon-to-oxygen ratio, specifically, can tell us whether the planet formed inside or outside the water ice line in the protoplanetary disk. WASP-39b likely formed several astronomical units from its star, perhaps beyond the ice line where water and other volatiles were frozen, and then migrated inward through gravitational interactions with the protoplanetary disk. Migration explains why hot Jupiters and hot Saturns exist at all. Giant planets can't form where we find them. There isn't enough material close to the star. They form farther out, accumulate massive atmospheres, then spiral inward over hundreds of thousands of years. WASP 39b's current orbit, just 0.0486 AU from its star, is the result of this migration process, halted when the protoplanetary disk dissipated or when tidal forces stabilized the orbit. One of WASP 39b's most puzzling features is its low density, only 0.19 g/cm superscript 3, less than 1/5 of Saturn's. Something is preventing the planet from contracting under its own gravity. Atmospheric inflation has been a puzzle since the first inflated hot Jupiters were discovered. The planet receives enormous stellar radiation, about 40 times what Jupiter receives from the Sun. Most of this energy is absorbed in the upper atmosphere. But to explain the large radius, energy must somehow be transported deep into the planet's interior, preventing gravitational contraction. Proposed mechanisms. Ohmic dissipation. Electric currents induced by the interaction of atmospheric winds with the planet's magnetic field generate heat deep in the interior. Kinetic energy deposition. Supersonic winds in the upper atmosphere slow down as they descend, converting kinetic energy to heat at depth. Enhanced opacity. Certain atmospheric constituents increase opacity to thermal radiation, trapping heat more efficiently. Tidal heating. Although WASP 39b's orbit is nearly circular now, residual tidal dissipation from past orbital evolution might contribute. WASP 39b's detailed atmospheric characterization helps test these mechanisms. Knowing the atmospheric composition, temperature structure, and circulation patterns constrains which energy transport processes are most important. This isn't just about WASP 39b. Understanding inflation helps us model planetary interiors throughout the galaxy. WASP 39b is one of hundreds of known gas giants, each with unique characteristics that collectively reveal patterns about planetary atmospheres. Comparative exoplanetology is essential. By studying many planets across different temperatures, masses, compositions, and stellar environments, we identify trends. For instance, at what temperature do clouds form? When do temperature inversions appear? How does stellar radiation affect atmospheric chemistry? WASP 39b, with its moderate temperature and comprehensive characterization, is a benchmark for comparison. Each planet occupies a specific region of parameter space. WASP 39b's temperature places it in a regime where photochemistry is active, clouds are patchy, and a diverse array of molecules can survive. Ideal conditions for atmospheric studies. WASP 39b will never host life. With temperatures exceeding 800 degrees Celsius, no liquid water, and a composition dominated by hydrogen and helium, it's utterly hostile to biology as we know it. Yet studying WASP 39b is essential for the search for life. Every atmosphere we characterize teaches us about atmospheric physics, chemistry, and evolution. The techniques we perfect on WASP 39b, transmission spectroscopy, eclipse observations, molecular identification, will be directly applied when we study potentially habitable planets. We're learning to read atmospheric spectra to distinguish biological from geological signals, to understand how planets interact with their stars. The detection of sulfur dioxide on WASP 39b, a photochemical product, has profound implications for biosignature detection. On Earth, photochemistry creates ozone from oxygen. Oxygen is produced by photosynthesis, life. Ozone protects that life from harmful UV radiation. But photochemistry can also create molecules that mimic biosignatures. Sulfur dioxide on WASP 39b is produced abiotically by photochemistry. We need to understand these abiotic processes so we don't mistake them for life when we observe temperate, rocky planets. Every photochemical pathway we identify, every molecule we detect on lifeless worlds, sharpens our ability to recognize genuine biosignatures. WASP-39b's atmospheric enrichment in heavy elements connects to broader questions about planet formation. There's a correlation between stellar metallicity, the abundance of elements heavier than hydrogen and helium, and giant planet occurrence. Metal-rich stars more frequently host giant planets because more solid material is available for building planetary cores. WASP-39b's atmosphere shows significant enrichment in carbon, oxygen, and sulfur, consistent with formation from a metal-enriched protoplanetary disk. This ties individual planetary properties to the conditions of their birth environments. Understanding these connections helps us predict where planets form, what compositions they have, and which systems might host rocky, potentially habitable worlds. JWST's initial observations of WASP-39b were just the beginning. Future observations will probe deeper. We can observe WASP-39b at higher spectral resolution to detect isotopes, different atomic masses of the same element, which provide clues about formation and evolution. We can monitor the planet over multiple orbits to search for temporal variability, changes in atmospheric features that might indicate weather. We can observe at different orbital phases to map temperature and composition variations across the planet's surface. Planned future observations. High-resolution spectroscopy. Detecting isotope ratios, e.g., deuterium to hydrogen, superscript 1, superscript 3c / superscript 1, superscript 2c, to constrain formation and atmospheric escape. Phase curve observations. Monitoring brightness as the planet orbits to map heat distribution and search for compositional variations. Time series monitoring. Observing multiple transits or eclipses to detect variability, indicating weather or atmospheric dynamics. Polarimetry. Measuring polarization of reflected starlight to detect clouds, hazes, and atmospheric structure. WASP-39b is a pathfinder. The techniques demonstrated on this world are now being applied to smaller, cooler planets, super-Earths, mini-Neptunes, and eventually, true Earth analogs. JWST is observing dozens of exoplanets across a range of sizes and temperatures. We're characterizing hot Jupiters, warm Neptunes, temperate super-Earths. Each observation builds our understanding of atmospheric diversity. WASP-39b showed us what's possible. Now we apply those capabilities to the full spectrum of planetary types. Among upcoming targets are planets in their stars' habitable zones, worlds where temperatures allow liquid water. These observations will test whether atmospheres can survive on planets around active M-dwarf stars, whether water vapor and carbon dioxide exist in temperate atmospheres, whether biosignature molecules can be detected. JWST isn't alone. The next generation of ground-based telescopes, the Extremely Large Telescope, the Giant Magellan Telescope, the 30-meter telescope, will achieve high-resolution spectroscopy that complements JWST's broad wavelength coverage. High-resolution ground-based spectroscopy can detect individual absorption lines for molecules, measure Doppler shifts caused by atmospheric winds, and map three-dimensional atmospheric structure. For WASP-39b, we can measure wind velocities, detect vertical atmospheric motion, and identify which layers of the atmosphere different molecules occupy. These observations complement JWST's lower resolution but higher sensitivity studies. Imagine descending toward WASP-39b. From space, it appears as a pale beige sphere, slightly smaller than Jupiter, dimly reflecting the yellow light of its star. As you approach, details emerge. Faint bands of clouds, subtle color variations from equator to poles. You enter the atmosphere at high altitude, where the pressure is barely measurable. Here, ultraviolet light from the star breaks apart molecules, photochemistry in action. Sulfur dioxide molecules float in a thin haze, created from hydrogen sulfide, rising from below. The sky is a strange, pale yellow, dimly illuminated by the star, which appears about 20% larger than our sun looked from Earth, but only 2/3 as bright. Descending deeper, you pass through layers of patchy clouds, silicate particles condensing from gaseous silicon and oxygen, forming mineral grains that drift in the wind. The temperature rises. At pressures equivalent to Earth's surface, the temperature exceeds 800 Kelvin, hot enough that metals would glow red. Deeper still, at pressures 10 or 100 times Earth's surface, the hydrogen atmosphere transitions from gas to supercritical fluid, neither clearly gaseous nor liquid. Water vapor, carbon dioxide, carbon monoxide swirl in turbulent currents. Lightning, if it exists, would arc through clouds of exotic composition, discharging electrical potential built up by atmospheric dynamics. You cannot descend farther. There is no surface, only ever-increasing pressure and temperature, transitioning eventually to a core of rock and ice compressed to exotic states. This is WASP 39b, a world of clouds and chemistry, shaped entirely by its star. WASP 39b is 700 light-years away. The light we detect today left the planet when Genghis Khan was conquering Asia. We will never visit WASP 39b. No spacecraft could survive the journey, let alone the environment. But we have done something perhaps more profound. We have analyzed its atmosphere in detail. We have identified its molecular constituents. We have measured temperatures, pressures, and chemical abundances. We understand how photochemistry transforms its air, how winds redistribute heat, how clouds form and dissipate. WASP 39b represents a triumph of human ingenuity. Decades of theoretical work, engineering innovation, and observational persistence came together to make these discoveries possible. We've demonstrated that we can study the atmospheres of alien worlds with the same detail we study planets in our own solar system. This is the dawn of comparative atmospheric science on a galactic scale. For all we've learned, mysteries remain. Does WASP 39b have a magnetic field? How do atmospheric properties vary with longitude and latitude? Are there undiscovered minor constituents, organic molecules, phosphine, exotic sulfur compounds? What drives the wind patterns? How efficiently does the atmosphere redistribute heat? Are there storms, vortices, atmospheric waves? How has the atmosphere evolved over the planet's lifetime? Has it lost mass to stellar winds? Will it continue to inflate, or will changing stellar conditions cause it to contract? These questions drive future research. Each observation refines our understanding. Each answer question raises new ones. Somewhere in the constellation Virgo, orbiting a star you'd need a telescope to see, WASP 39b continues its eternal dance. Every 4.05 days, every 97 hours, it completes another orbit. The day side bakes. The night side cools. Winds race between them at thousands of kilometers per hour. Clouds form and dissipate. Photochemistry transforms molecules high in the atmosphere. WASP 39b is one planet among thousands. But it holds a special place in history. The first exoplanet where James Webb revealed the full richness of atmospheric chemistry, demonstrating what's possible in a new era of exoplanet science. This is just the beginning. Hundreds of planets await characterization. Dozens will be observed in coming years, each revealing its own atmospheric secrets. And someday, perhaps soon, we will observe a rocky planet in its star's habitable zone, detecting water vapor, carbon dioxide, oxygen, perhaps even biosignature molecules. When that moment comes, we will draw on everything learned from WASP 39b. Every technique, every model, every hard-won piece of atmospheric knowledge will guide our interpretation. The cloud world has taught us to read the atmospheres of alien planets. Now we turn those lessons toward the ultimate question. Are we alone? If you enjoy planets that might harbor life, then you're going to really enjoy Kepler 22b, The First Hope and the Discovery of New Earths. December 5th, 2011. After nearly 3 years of staring unblinking at a patch of sky, NASA's Kepler Space Telescope had a story to tell. Among the hundreds of planet candidates it had detected, one stood out, a world larger than Earth, orbiting a star remarkably similar to our Sun, at a distance where temperatures might allow liquid water to exist on its surface. We are announcing today the confirmation of Kepler 22b, the first confirmed planet in the habitable zone of a Sun-like star. This planet, roughly 2.4 times Earth's radius, orbits its star every 290 days. We don't yet know if Kepler 22b has a rocky surface or oceans, but we know it exists in the region where liquid water could persist, the first step toward habitability. For the first time in human history, we had confirmed evidence of a planet, not around a tiny red dwarf or an exotic pulsar, but around a star like our own Sun, orbiting in the habitable zone where conditions might support life. This is the story of Kepler 22b, the first hope, the world that changed our search for life beyond Earth. The story of Kepler 22b begins long before its discovery, with a vision, a stubborn scientist, and a question. Are Earth-like planets common? In the 1990s, we knew of no planets beyond our solar system. Many astronomers doubted Earth-like planets existed, or if they did, whether we could detect them. I proposed a mission, a space telescope that would stare at one patch of sky continuously, monitoring hundreds of thousands of stars, searching for the tiny dimming that occurs when a planet crosses in front of its star. NASA rejected the proposal 4 times. They said the technology wasn't ready, the precision impossible. But Barucki persisted. Advances in CCD detector technology made the measurements feasible. In 2001, NASA selected Kepler as a discovery mission. 8 years later, on March 6, 2009, a Delta II rocket carried Kepler into an Earth-trailing heliocentric orbit. Kepler was designed with singular purpose: find Earth-sized planets in the habitable zones of Sun-like stars. Kepler monitored approximately 150,000 stars simultaneously in a 115 square degree field of view, about the size of your hand held at arm's length. It took images every 30 minutes for most stars, and every minute for about 500 high-priority targets. This continuous monitoring allowed us to detect multiple transits of planets with orbital periods ranging from days to years. To detect an Earth-sized planet transiting a Sun-like star requires measuring brightness changes of about 0.008%, roughly 80 parts per million. For a planet in the habitable zone, orbiting once per year, at least 3 transits, 3 years of observations, would be needed for confirmation. Kepler's precision was unprecedented. Its photometer could detect changes as small as 20 parts per million. But precision alone wasn't enough. Stability was critical. Kepler's spacecraft had to remain incredibly stable. Any wobble would mimic a planetary transit. The reaction wheels maintaining spacecraft pointing had to be precise. The temperature had to be controlled to prevent thermal expansion of the telescope. Every aspect was engineered for one goal: photometric precision over years. Within months, Kepler detected planet candidates. By January 2010, the first batch was announced: 5 hot Jupiters, giant planets orbiting extremely close to their stars, easy to detect because of their short periods and large sizes. But the team knew these were just the beginning. Hidden in the data were smaller planets, longer period planets, and, potentially, Earth-like planets in habitable zones. Among the thousands of stars monitored was one cataloged as KIC 10593626, later designated Kepler 22. This star, located approximately 640 light-years away in the constellation Cygnus, was showing a very faint, very interesting signal. Remarkably, Kepler observed Kepler 22b's first transit within days of beginning science observations, but no one knew it yet. The very first data set included a transit of Kepler 22b, but you can't confirm a planet from a single transit. You need to see it repeat with regular periodicity. We had to wait nearly a year for the second transit and another year for the third. Only then could we be confident we were seeing a genuine planet rather than an instrumental artifact or eclipsing binary star. The signal was subtle. The planet blocked only about 0.04% of the star's light, far less than hot Jupiter's, but detectable with Kepler's precision. The period was approximately 290 days, placing the planet's orbit squarely in the potentially habitable zone. Detecting a signal is one thing. Confirming it's a genuine planet is another. False positives abound. Eclipsing binary stars, background stars, instrumental artifacts. We used ground-based telescopes to check for stellar companions that might be causing the signal. High-resolution imaging revealed known nearby stars within the Kepler aperture that could be eclipsing. Spectroscopic observations characterized the host star, its temperature, radius, mass, allowing us to confirm the planet's properties. Radial velocity observations checked for stellar wobbles consistent with a planetary companion. The radial velocity signal was too small to measure with existing instruments. A planet of Kepler 22b size and orbital distance produces a stellar wobble of less than 1 meter per second at the edge of detection capability for Sun-like stars. But statistical validation and the lack of any alternative explanation gave confidence. We used statistical validation techniques, calculating the probability that the signal could be caused by something other than a planet. For Kepler 22b, the false positive probability was extremely low. Combined with the lack of detected companions and the consistency of the transit timing, we confirmed it as a planet with high confidence. Kepler 22 is a G5e star, slightly smaller, cooler, and older than our Sun, but more similar to the Sun than any other star known to host a habitable zone planet at the time of discovery. Kepler 22 is what we call a solar analog, a star similar enough to the Sun that planets orbiting it would experience comparable stellar environments. This similarity is crucial for assessing habitability. We understand how solar-type stars behave, how their radiation affects planets, how stable they are over billions of years. Kepler 22b's host star made it the most Sun-like habitable zone planet host discovered at that time. From Kepler's transit observations and stellar characterization, we derive fundamental properties of Kepler 22b, but significant uncertainties remain. Kepler 22b sits in an interesting size range. Below about 1.5 Earth radii, planets tend to be rocky like Earth. Above about 2.0 Earth radii, many planets have thick hydrogen-helium atmospheres, making them mini-Neptunes. At 2.4 Earth radii, Kepler 22b could be either a large rocky planet with a thick atmosphere, a water world with deep oceans, or a small gas planet. Without mass measurements, we can't know for certain. The habitable zone is defined as the range of orbital distances where a planet could have liquid water on its surface. Not too hot that water boils away, not too cold that it freezes solid. Calculating the habitable zone boundaries depends on several factors: stellar luminosity, planetary albedo, how reflective the planet is, and atmospheric greenhouse effect. For Kepler 22, with 79% of the Sun's luminosity, the habitable zone extends roughly from 0.72 to 1.4 AU. Kepler 22b, at 0.812 AU, orbits near the inner edge, comparable to Venus's orbit in our system, but receiving less total radiation because the star is dimmer. Kepler 22b receives about 25% more stellar flux than Earth receives from the Sun. More than Earth, but less than Venus. Whether this is habitable depends critically on the planet's atmosphere. If Kepler 22b has a thin atmosphere like Earth's, surface temperatures might be below freezing without a substantial greenhouse effect. But if it has a thick CO2 atmosphere like Venus, it could be too hot for habitability despite the lower stellar flux. The answer lies in understanding what kind of planet Kepler 22b actually is. Without mass measurements, astronomers have proposed several scenarios for Kepler 22b's composition, each with different implications for habitability. Scenario 1. Rocky super-Earth. If Kepler 22b is primarily rocky, composed of iron and silicates like Earth, its mass would be approximately 10 to 15 Earth masses, giving it a density around 5 grams per cubic centimeter. The surface gravity would be about 2 to 3 times Earth's, and the planet would likely have a thick atmosphere retained by its strong gravity. Tectonic activity, volcanism, and a magnetic field generated by a molten core are all plausible. A rocky Kepler 22b might have continents and oceans, active geology, and potentially the ingredients for life. But there's a catch. At 2.4 Earth radii, it's larger than most confirmed rocky planets. The transition from rocky to gaseous planets occurs somewhere between 1.5 and 2.5 Earth radii, and Kepler 22b sits right in this uncertain regime. Scenario 2. Water world/ocean planet. Kepler 22b could be a water world, a planet where water comprises a significant fraction of its mass. These planets might form beyond the ice line in protoplanetary disks where water ice is abundant, then migrate inward. With perhaps 50% water by mass, Kepler 22b could have oceans hundreds of kilometers deep, possibly with exotic high-pressure ice phases at the bottom and a steam or water vapor-rich atmosphere above. On such a world, there would be no land, no continents, no dry surface. Life, if it exists, would be purely oceanic, adapted to high pressures, or floating in the atmosphere. The absence of a rock-water interface, where many important chemical cycles occur on Earth, might affect habitability. Scenario 3. Mini-Neptune. The third possibility is that Kepler 22b is a mini-Neptune, a planet with a rocky or icy core, surrounded by a thick hydrogen-helium atmosphere comprising 10% or more of the planet's mass. At this size, many planets have such atmospheres. If Kepler 22b is a mini-Neptune, it would have no solid surface accessible to us, and the hydrogen atmosphere would extend hundreds of kilometers deep. A mini-Neptune Kepler 22b would not be habitable in the traditional sense. No solid or liquid surface for life as we know it. However, at sufficient depth, temperatures and pressures might allow liquid water to exist within the hydrogen atmosphere, creating unusual conditions unlike anything in our solar system. Determining which scenario is correct requires measuring Kepler 22b's mass, and that has proven extraordinarily difficult. The radial velocity signal for Kepler 22b should be less than 1 meter per second, about walking speed. Detecting such a small wobble in a sun-like star is at the very edge of our capabilities. Sun-like stars have complex surfaces, convection, granulation, oscillations, that create noise-mimicking radial velocity signals. For Kepler 22, which is faint at magnitude 11.7, we need large telescopes and many observations to average out the noise. Despite extensive efforts by multiple teams using instruments like HIRES on Keck and HARPS at La Silla, a definitive mass measurement has remained elusive. Statistical estimates based on the planet's radius suggest a mass anywhere from 5 to 40 Earth masses, a huge range encompassing all three compositional scenarios. The question that captivated the world in 2011 remains: could Kepler-22b harbor life? Habitability requires several ingredients: liquid water, energy sources, appropriate chemical elements, carbon, nitrogen, phosphorus, sulfur, and a stable environment over long timescales. Kepler-22b orbits in the habitable zone, suggesting liquid water might exist. The star is stable, older than the Sun, giving life time to develop. But without knowing the planet's composition and atmospheric properties, we can't assess habitability definitively. If Kepler-22b is rocky or a water world, its atmosphere would be key to habitability. A thin nitrogen-oxygen atmosphere with moderate CO2, like Earth's, would allow temperate conditions. Water vapor would provide greenhouse warming, potentially raising surface temperatures above freezing despite the planet's greater distance from its star. A thicker CO2 atmosphere, like early Mars might have had, could create more warming but also higher surface pressures. But there's a danger. At Kepler-22b's stellar flux level, a runaway greenhouse effect, where increasing temperatures vaporize more water, which causes more warming, which vaporizes more water, could render the planet uninhabitable, like Venus. The boundary between habitable and runaway greenhouse is sensitive to many factors. Clouds provide cooling by reflecting sunlight. Ocean heat capacity moderates temperature swings. The planet's rotation rate affects heat distribution. Without observational data, we're working with models that have large uncertainties. The ultimate answer to Kepler-22b's habitability lies in observing its atmosphere, detecting which molecules are present and measuring their abundances. Characterizing Kepler-22b's atmosphere is extremely challenging. The planet is 640 light-years away, the star is relatively faint, and the transit depth is only 0.04%. Even with the James Webb Space Telescope, detecting atmospheric features would require many transits and perfect conditions. JWST's resources are limited, and many closer, brighter targets take priority. Hubble Space Telescope observations of Kepler-22b have been attempted but yielded inconclusive results. The signal is simply too faint. Future facilities, larger space telescopes, next-generation ground-based observatories with adaptive optics might eventually reveal Kepler-22b's atmospheric secrets. But for now, the planet remains a tantalizing mystery. Kepler-22b was not the last habitable zone planet Kepler would find. It was the first of many. After Kepler-22b, we announced dozens of other habitable zone candidates. Kepler-62f, Kepler-186f, Kepler-442b, Kepler-452b. Each discovery refined our understanding of how common such planets are. By mission's end, Kepler had identified over 50 planets and candidates in their star's habitable zones. The answer to the question, are Earth-like planets common, is yes. They appear to be abundant. Kepler-22b pioneered the search. It demonstrated that Kepler could detect habitable zone planets around Sun-like stars. It captured public imagination and galvanized support for exoplanet research. It changed the conversation from do habitable planets exist to how do we study them? Beyond individual discoveries, Kepler's data revealed statistical truths about planetary systems. By analyzing the full Kepler dataset, we calculated occurrence rates, how often planets of different sizes exist at different orbital distances. For planets between 0.75 and 1.5 Earth radii in the habitable zones of Sun-like stars, the occurrence rate is approximately 20% to 50%. That means 1 in 5 to 1 in 2 Sun-like stars hosts a potentially Earth-like planet. Extrapolating across the galaxy, with 100 billion Sun-like stars, this suggests tens of billions of potentially habitable planets in the Milky Way alone. Kepler 22b was not an anomaly. It was one of countless worlds. Kepler 22b and planets like it inspired the next generation of missions designed to find and characterize Earth-like worlds. TESS, Transiting Exoplanet Survey Satellite, launched 2018, surveying bright nearby stars for transiting planets ideal for atmospheric characterization. Plato, Planetary Transits and Oscillations of Stars. European mission plan for 2026, searching for Earth-sized planets in habitable zones around Sun-like stars. Habitable Worlds Observatory. Proposed NASA flagship mission for the 2040s, designed to directly image and characterize dozens of Earth-like planets. Kepler changed everything. Before Kepler, we hoped Earth-like planets existed, but had no evidence. Kepler proved they're common. Now the challenge is characterization, studying atmospheres, detecting biosignatures, determining which planets are truly habitable. Kepler 22b showed us the goal is real and achievable. Over a decade after its discovery, fundamental questions about Kepler 22b remain unanswered. What is its mass and composition? Rocky super-Earth? Water world? Mini-Neptune? The answer determines everything else. Does it have an atmosphere? If so, what molecules does it contain? How thick is it? What is the surface temperature? Are conditions temperate, frozen, or runaway greenhouse? Does it have a magnetic field, which would protect an atmosphere from stellar wind stripping? Is there surface water, oceans, ice caps, or none at all? Could it support life? The ultimate question, one we may not answer for decades. Kepler 22b is both a triumph and a challenge. We know it exists. We know it orbits in the habitable zone, but we don't know if it's habitable, and with current technology, we can't find out. It's a reminder of how far we've come and how far we have to go. Future instruments might eventually characterize Kepler 22b, or more likely, will study closer, brighter analogs discovered by TESS and future missions. The next generation of ground-based telescopes, the 30 to 40 meter class, combined with advanced adaptive optics and high-resolution spectroscopy, will push the boundaries of what's detectable. Space-based missions optimized for direct imaging will observe Earth-like planets in reflected light, measuring colors, cloud patterns, seasonal variations, biosignatures if they exist. Kepler 22b itself may remain beyond reach. At 640 light-years, it's distant enough that even future observatories will struggle to characterize it. But the lessons it taught, the methods developed, the theories tested, apply to every habitable zone planet we discover. Somewhere in the constellation Cygnus, 640 light-years from Earth, Kepler 22b continues its orbit. Every 290 days, every earthly season, it completes another circuit around its sun-like star. We don't know what it looks like. We don't know if it has oceans or continents, clouds or clear skies, a rocky surface or endless depths. We don't know if it's warm or cold, habitable or hostile. But we know it exists, and that knowledge changed us. Before Kepler 22b, habitable zone planets around sun-like stars were speculation. After Kepler 22b, they became reality, statistically common, physically confirmed, waiting to be studied. Kepler 22b was the first hope, the first confirmed world where conditions might allow liquid water on a planet orbiting a star like our Sun. It wasn't the last. It wasn't even the best candidate, but it was the first, and that matters. Today, children grow up knowing that planets in habitable zones exist. They know that Earth is not unique in its orbit or its star. They know that the question is not, are there other worlds like ours? But, how do we study them? How do we find life if it's there? This is Kepler 22b, the first confirmed habitable zone planet around a sun-like star. A super-Earth of uncertain composition. A world that might be rocky or watery or gaseous. a planet that might be warm or cold, dead or alive. A mystery, a hope, a beginning. The search continues. The discoveries multiply, and the universe always holds more wonders than we imagine. For our next planet today, we're investigating K2-291b and the super-Earth mystery. In May 2013, NASA's Kepler Space Telescope, the most successful planet-hunting mission ever flown, faced catastrophe. After 4 years of unprecedented discoveries, a second reaction wheel failed. Without at least 3 functioning wheels, Kepler could no longer maintain the precise pointing necessary for its primary mission. The original Kepler mission was over, but the story wasn't finished. In 2014, Kepler was reborn as K2, the second light. Using the pressure of sunlight to balance the spacecraft, engineers achieved enough stability to continue hunting planets, observing new fields every 80 days. Over 4 years, K2 would discover hundreds of new worlds, including one that exemplifies the mysteries of planetary science, K2-291b, a super-Earth larger than our planet but smaller than Neptune. A world whose very existence poses questions about how planets form, what they're made of, and where the line between rocky and gaseous worlds truly lies. K2's second life required compromise and creativity. The spacecraft could no longer stare at a single field for years. Instead, it observed different regions of the sky for approximately 80 days each, one campaign at a time. K2 gave us breadth instead of depth. The original Kepler mission observed one patch of sky deeply, finding planets with years-long orbital periods. K2 surveyed many different fields, sampling diverse stellar populations, young stars, old stars, stars in clusters, binary systems. We couldn't find planets with Earth-like one-year orbits, but we found tremendous diversity in shorter period planets. From 2014 through 2018, K2 observed 19 campaigns, monitoring over 500,000 stars and discovering more than 500 confirmed planets. Among these discoveries was K2-291b, a planet found during Campaign 15 in 2017. Campaign 15 ran from August 23rd to November 20th, 2017, observing a field rich in stars near the galactic center direction. Among the approximately 23,000 targets was EPIC 2-468511721, later designated K2-291. K2-291 caught our attention because of a clear, repeating transit signal every 2.23 days. The transit depth of approximately 0.2% suggested a planet in the super-Earth to sub-Neptune size range. Between Earth and Neptune in size, a population we're particularly interested in understanding. The regularity and shape of the transit looked genuine, not an eclipsing binary or instrumental artifact. K2's photometric data revealed K2-291b through the transit method. The planet passes between its star and Earth every 2.23 days, blocking a small fraction of starlight and creating a detectable dimming. For K2-291b, we observed 3 clear transits during the 80-day campaign. The period was well-determined, 2.2285 days. The transit depth told us the planet's radius relative to the star, approximately 2.5 Earth radii. The transit duration and shape gave us information about the orbital geometry and confirmed the signal was consistent with a transiting planet. But detection is just the beginning. Every candidate must be vetted to eliminate false positives, background eclipsing binaries, blended stars, or instrumental effects that mimic planetary transits. Confirming K2-291b required multiple lines of evidence from ground-based observations. We used high-resolution imaging with adaptive optics to search for nearby stellar companions, that could contaminate the K2 aperture. We found no companions close enough to produce the observed transit signal. Spectroscopic observations characterized the host star, measuring its temperature, radius, metallicity, and confirming it's a single star, not a binary. Ground-based photometry attempted to detect transits with better spatial resolution, confirming the signal originates from K2-291 itself. Radial velocity measurements, detecting the star's wobble caused by the planet's gravity, would provide the planet's mass and confirm the detection definitively. But K2-291, with an apparent magnitude of approximately 12.5, is relatively faint, making precise radial velocity measurements challenging. For many K2 discoveries, especially around fainter stars, we use statistical validation rather than waiting for radial velocity confirmation. We calculate the probability that the signal could be caused by something other than a planet, an eclipsing binary, a background star, or other astrophysical false positive. For K2-291b, the false positive probability was very low, allowing us to validate it as a planet with high confidence. K-dwarf stars are particularly interesting for exoplanet studies. They're more common than Sun-like G-type stars. They're more stable than the smallest M dwarfs, which can produce violent flares, and they live for tens of billions of years, much longer than the Sun's 10-billion-year lifespan. K2-291 represents a typical K-dwarf, mature, stable, and a good host for planetary system studies. K2-291b is classified as a super-Earth, a planet larger than Earth but smaller than Neptune. But this classification hides tremendous uncertainty about the planet's true nature. At 2.45 Earth radii, K2-291b sits right at a critical transition. Planets smaller than about 1.5 Earth radii tend to be rocky like Earth and Mars. Planets larger than about 2.5 Earth radii often have thick hydrogen-helium atmospheres, like Neptune. K2-291b is right in between, in a size range where composition can vary dramatically. Without mass measurements, we can't know if it's a large rocky world, a water world, or a small gas planet. One of Kepler and K2's most important discoveries is the Radius Valley, or Fulton Gap, a relative scarcity of planets between approximately 1.5 and 2.0 Earth radii, first identified by Benjamin Fulton at Caltech in 2017. The Radius Valley divides two distinct planetary populations. Below the valley, around 1.0 to 1.5 Earth radii, we find rocky planets, super-Earths with iron cores and silicate mantles, similar to Earth's composition. Above the valley, from 2.0 to 4.0 Earth radii, we find subneptunes or mini-Neptunes, planets with rocky cores but substantial hydrogen-helium atmospheres. The valley exists because of atmospheric loss. The leading explanation is that planets form with primordial hydrogen-helium atmospheres from the protoplanetary disk. Close to their stars, these atmospheres are heated and can escape to space, driven by the planet's own internal heat or by stellar radiation. Planets that lose their entire atmosphere drop below the valley, becoming bare rocky cores. Planets that retain atmospheres remain above the valley as subneptunes. K2-291b, at 2.45 Earth radii, sits above the valley. This suggests it either has a substantial gaseous envelope that it's managed to retain, or it's a water world with deep oceans and a steamy atmosphere, or it's a rocky planet on the large end of what's possible. Each possibility has different implications for the planet's formation and evolution. In the first scenario, K2-291b is primarily rocky, composed of iron and silicates like Earth, but scaled up in size and mass. If K2-291b is rocky, its mass would be approximately 8 to 12 Earth masses, giving it a density around 5.5 to 6.0 grams per cubic centimeter, similar to Earth's density. The surface gravity would be approximately 2 to 2.5 times Earth's. Such a planet could have active plate tectonics, a molten core generating a magnetic field, and a substantial atmosphere retained by its strong gravity. But at 900 to 1000 Kelvin, hotter than Venus, K2-291b would be far too hot for liquid water on its surface. The planet orbits 30 times closer to its star than Earth orbits the Sun. Any atmosphere would likely be dominated by vaporized rock and heavy gases. At these temperatures, we'd expect an atmosphere of sodium, potassium, silicon monoxide, perhaps even vaporized metals. The surface, if accessible, would glow red-hot. Magma might cover parts of the surface. This would be a lava world. Rocky, yes, but nothing like Earth's temperate environment. The second scenario envisions K2-291b as a water world, a planet where water comprises a significant fraction of its mass. Water worlds might form in the outer regions of protoplanetary disks where water ice is abundant, then migrate inward. At 2.45 Earth radii, K2-291b could have a rocky core surrounded by hundreds of kilometers of water, liquid at depth, transitioning to high-pressure ice phases deeper still, and a thick steam atmosphere above. Water could comprise 30% to 50% of the planet's mass. At K2-291b's temperature, the surface would not be a tranquil ocean. Instead, the water would exist as supercritical fluid, neither clearly liquid nor gas, at high temperatures and pressures. A thick steam atmosphere hundreds of kilometers deep would shroud the planet. Such worlds challenge our notions of habitability. There's no solid surface. The environment is extreme, hot, high pressure, with chemistry unlike Earth's oceans. Yet water is abundant, and at certain depths, temperatures and pressures might allow interesting chemistry. Life, if it could exist, would be radically different from anything on Earth. The third possibility is that K2-291b is a subneptune, a planet with a rocky or icy core surrounded by a thick hydrogen-helium atmosphere comprising 5% to 20% of the planet's mass. Subneptunes are the most common planetary type discovered by Kepler and K2, yet they don't exist in our solar system. They represent a distinct planetary category. If K2-291b is a subneptune, it would have a mass around 7 to 10 Earth masses, with a substantial gaseous envelope. The hydrogen atmosphere would extend hundreds of kilometers before transitioning to higher pressure molecular hydrogen, eventually reaching the rocky/icy core. A subneptune K2-291b would have no solid or liquid surface in the traditional sense. Descending through the atmosphere, pressure and temperature would increase continuously until hydrogen transitions to supercritical fluid, then to metallic phases at extreme depths. Understanding subneptunes is crucial because they're so common. Why don't we have one in our solar system? How do they form? Can they retain their atmospheres over billions of years? K2-291b is one of hundreds of subneptunes we need to characterize to answer these questions. The single most important unknown about K2-291b is its mass. Mass, combined with radius, gives density, and density reveals composition. Density is the key diagnostic. A planet with 2.45 Earth radii but 5 Earth masses would have a density around 2g/cm superscript 3, consistent with a water world. The same radius but 10 Earth masses gives 4g/cm superscript 3, consistent with a rocky planet with some volatiles. And 15 Earth masses gives nearly 6g/cm superscript 3, a dense, iron-rich rocky world. We can't distinguish these scenarios without measuring mass. Measuring K2-2 K2-91b's mass requires the radial velocity method, detecting how much the planet's gravity causes its star to wobble. As K2-291b orbits, it gravitationally tugs on its star. The star and planet orbit their common center of mass. For K2-291, depending on the planet's mass, this causes the star to move toward and away from us at speeds of roughly 2 to 8 meters per second, walking to jogging speed. We detect this motion through Doppler shifts in the star's spectral lines. But measuring velocities of a few meters per second requires extraordinary precision, and K2-291 presents challenges. K2-291, at magnitude 12.5, is relatively faint. K-dwarf stars have many molecular absorption lines in their spectra, which is good for radial velocity precision, but they can also be magnetically active with star spots that create velocity variations mimicking planetary signals. We need multiple observations over many orbital periods to average out noise and extract the genuine planetary signal. As of current knowledge, comprehensive radial velocity measurements of K2-291b have not been published. This is common for K2 discoveries. Hundreds of validated planets await detailed characterization. There's a backlog of K2 planets deserving follow-up. We prioritize based on scientific interest, observability, and resource availability. K2-291b is scientifically interesting because of its size, but it competes with hundreds of other targets. Radial velocity observations are time-intensive. We might need 10 to 20 observations spread over months to determine mass with confidence. Statistical mass-radius relationships, derived from planets where both mass and radius are known, suggest K2-291b's mass is most likely between 7 and 12 Earth masses. But until direct measurements confirm this, the planet's composition remains uncertain. If K2-291b has an atmosphere, whether rocky planet atmosphere, steam atmosphere, or hydrogen-helium envelope, could we detect and characterize it? Atmospheric characterization requires transmission spectroscopy during transits or emission spectroscopy during secondary eclipses. For K2-291b, the transit depth is about 0.2%, and atmospheric features might change this depth by parts per thousand. The host star is faint at magnitude 12.5, meaning fewer photons to collect. These factors make atmospheric characterization challenging, but not impossible with instruments like JWST. K2-291b is not currently a top priority JWST target. Brighter host stars and larger planets are being observed first. But as JWST continues operations, planets like K2-291b could be observed, especially if they represent interesting test cases for atmospheric models. At 900 to 1000 Kelvin, K2-291b is hot enough to vaporize lead, too hot for liquid water, but cooler than ultra-hot Jupiters. Like all close-orbiting planets, K2-291b is likely tidally locked, one hemisphere permanently facing the star, the other in darkness. Tidal locking creates extreme day-night temperature contrasts. The day side receives constant stellar radiation, heating to perhaps 1,100 to 1,200 K. The night side, receiving no direct starlight, might cool to 600 to 800 K. These temperature differences drive atmospheric circulation, winds flowing from hot day side to cool night side, redistributing heat. The efficiency of heat redistribution depends on atmospheric mass and composition. A thick hydrogen atmosphere transports heat efficiently. A thin rocky atmosphere less so. The day-night temperature difference, measurable through phase curve observations, could reveal which type of atmosphere K2-291b possesses. K2-291b is one of dozens of super-Earths discovered by the K2 mission. Together, these planets are revealing patterns about how planetary systems form and evolve. K2 discovered over 150 planets between 2 and 3 Earth radii, the super-Earth to sub-Neptune range. By studying this population statistically, we've learned that these planets are incredibly common. On average, small planets outnumber gas giants by factors of 10 or more. Understanding what these planets are made of, why they're so common, and how they form is one of the most important questions in exoplanet science. Each super-Earth discovered by K2 adds to our statistical understanding, each one characterized through mass measurements or atmospheric observations refines our models. How do super-Earths like K2-291b form? And why do so many orbit close to their stars when our solar system has none? Super-Earths likely form through the same core accretion process as larger planets. Dust grains collide and stick together, forming pebbles, then planetesimals, then planetary embryos. These cores accrete gas from the protoplanetary disk. If they accrete a lot of gas, they become gas giants. If they accrete modest amounts before the disk dissipates, they become sub-Neptunes. If they lose their atmospheres later, they become rocky super-Earths. K2-291b's close orbit, 0.032 AU, just 4.8 million kilometers from its star, suggests migration. The planet likely formed farther out where more material was available, then spiraled inward through gravitational interactions with the disk or with other planets. Understanding migration mechanisms is crucial. Did K2-291b migrate smoothly through the disk, or was it flung inward by gravitational encounters with other planets? The current circular orbit suggests smooth migration, but we need to find additional planets in the system to confirm the migration history. K2-291 might host additional planets. Multi-planet systems are common, and K2's 80-day observation window might have missed planets with longer periods or different orbital alignments. We've searched K2-291's light curve for additional transits and found no clear signals. But that doesn't mean there are no other planets. They might not transit from our viewing angle, or they might have periods longer than 80 days, or they might be too small to detect with K2's precision. Radial velocity monitoring or longer duration photometry for missions like TESS could reveal hidden companions. Transit timing variations, deviations from perfectly periodic transits caused by gravitational interactions with other planets, could also reveal unseen worlds. For K2-291b, with only 3 observed transits, timing variations are not yet detectable. But future observations could change that. K2-291b exists 900 light-years away, a distance light travels in 9 centuries. The photons we detected from its transits in 2017 left the system when a Mongol empire was at its height. We will never visit K2-291b. We will likely never even see it directly. But we know it's there. We don't know what it looks like. Rocky surface glowing red-hot? Endless ocean beneath thick steam clouds? Gaseous hydrogen atmosphere with no defined surface? Each possibility is plausible given the current data. This uncertainty is not failure. It's the frontier of science. Every planet we discover expands the boundaries of what we know. Every characterization fills in details. Every mass measurement, every atmospheric spectrum, every orbital refinement brings the picture into sharper focus. Even without mass measurements or atmospheric observations, K2-291b teaches us important lessons. K2-291b confirms that super-Earths are common around K-dwarf stars. It demonstrates that planets can survive very close to their host stars without being destroyed. It provides a data point for statistical studies of the radius distribution and occurrence rates. and it represents the kind of planet that future missions will characterize in detail. K2-291b is not unique. It's representative. One of hundreds of similar planets discovered by K2, one of thousands of super-Earths in the galaxy. Yet each individual planet matters because together they reveal the patterns. Future missions will build on K2's legacy, discovering more planets and characterizing them in greater detail. Planetary transits and oscillations of stars. European mission launching 2026 will discover and characterize planets around bright stars with better precision than K2. Transiting Exoplanets survey satellite. Already operating, finding planets around even brighter stars than K2 observed. Ideal for follow-up. Extremely large telescopes. 30 to 40 meter ground-based telescopes will achieve radial velocity precision of 10 centimeters per second, measuring masses of small planets precisely. Future space observatories. Next-generation missions will directly image and characterize nearby super-Earths, revealing surface features and atmosphere composition. Planets like K2-291b are stepping stones. K2 found them, proved they exist in abundance. Now we develop the tools to study them thoroughly. Mass measurements, atmospheric characterization, detailed modeling. Eventually, we'll understand not just that super-Earths exist, but what they're made of, how they form, and whether any could support life. Somewhere in the constellation Scorpius, 900 light-years distant, K2-291b continues its orbit. Every 2.23 days, every 53.5 hours, it completes another circuit. One hemisphere bakes under constant starlight. The other cools in eternal night. Between them, the terminator, where conditions might be less extreme. We don't know if K2-291b is rocky or watery or gaseous. We don't know its mass or density. We don't know if it has an atmosphere or what that atmosphere might contain. But we know enough to wonder, and wonder drives discovery. K2-291b represents a universe of possibilities, a reminder that beyond our solar system, nature has crafted worlds in configurations we never imagined. Super-Earths don't exist in our planetary system, yet they're the most common planetary type in the galaxy. K2 found hundreds of planets during its second life, a mission that almost ended but was resurrected through ingenuity and determination. Among those discoveries, K2-291b stands as one of many mysteries waiting to be solved. Someday, perhaps years from now, perhaps decades, we will measure K2-291b's mass. We will determine its composition. We might even detect its atmosphere, reading the chemical signatures of a world we'll never touch. And that knowledge will be another step in humanity's journey to understand the cosmos and our place within it. This is K2-291b, a super-Earth, a mystery, a reminder that the universe contains wonders beyond counting, and that the search to understand them continues. If you made it all the way through this video, thank you so much. It really does mean all the worlds to me. Make sure to like, subscribe, and leave a comment about what exoplanet I should cover in the next video. I'll see you tomorrow, and thank you for watching.